second argument to, oh, okay, meeting being recorded. Thank you for recording it, Andrew. I know there's a lot of appetite for that. I give it as the second argument to the map function. You don't have to put the open close parentheses at the end. That is what's referred to as calling the function. You really just have to give the function name. It gets called later. You don't have to do it in map. Map does it for you. So map is kind of the heart of the purrr library, but there are a lot of different variations, which I'll touch on real quickly. And I'll get into kind of why this came up. So I learned R a long time ago in college, and the tidyverse didn't exist at the time when I learned it, which actually makes me feel like a little bit old. When I was in college, I learned this suite of functions that exist in base R called apply, and sometimes there are letters that precede apply, L apply, T apply, S apply, to name a few. I think there are many more. And I could never quite keep things straight when it came to apply. I couldn't quite figure out what went into the applies, what came out of the applies. Each function is a little bit different. I would always be looking up the help documents for each of these. I could use them, but I could never really commit to memory how to use them. Purrr has taken this apply, this kind of functional programming style suite of functions, and has created a new suite of functions that I think has very readable, literate names. This is kind of a common thing in the entire tidyverse. Things have verbs, you are mutating, you are summarizing, in this case, you are mapping. And there's a format to how these functions work. So every purrr function typically has two parts. The name of the purrr function has two parts. The first part is for the number of the inputs that go into the function. And the second part is the type of the output that you get. So there's really three ways to specify the number of inputs. Broadly speaking, there's a way to pass one input, there's a way to pass two, and then there's a way to pass more than two, is kind of the three families here. And those functions are called map, which we have looked at. This is kind of the heart of the library, map2, and pmap. And the functions all work the same way, but it's really just in the number of inputs that go into it. Map takes one input, like we saw above. It took just my list. Map2 will take two equally sized inputs. So say you had one collection of 100 things and another collection of 100 things, and the first item in each list corresponded to each other, the second item in each list corresponded to each other, and you needed to work over the pairs in parallel. This might be a case for map2, and then you pass two arguments, and the function always goes last, or really after the input vectors. And finally, there's pmap for things that when you want to work on more than two things. Pmap kind of has the syntax of map in that there's only one argument with the collection, and it's a list, but it's a nested collection, which will have, you likely need it when you need to work on three or more things. So if you're taking the map2 example and extending it, if you need anything more than two, use pmap. Your first argument needs to be now a list, which is just one item as opposed to two or three or four or five. They all have to be the same size, just like map2. And the function comes afterward. Let me just check the chat again real quickly. Oh, difference between a list and a vector. I was supposed to cover that. A vector in R is a collection of, it's a homogeneous collection is how I like to think about it. It has many different things, and they all have to be the same type. And there are a few basic R types: character, logical, you may call it Boolean, integer, double, which you may call floating point, maybe one that I'm forgetting. And everything in the vector has to be the same. That's a rule. They're called atomic vectors, I believe, in R speak for that reason. A list can be a heterogeneous collection. It can have single values, an integer, a true false value, a floating point value, what have you. It can have vectors, those homogeneous types I just talked about. It can even have lists themselves inside of lists. And lists are kind of the most flexible data structure in R. You can almost always use a list because you can just shove whatever you want to in it. When you're working in the tidyverse, you are generally getting these objects returned. We'll look at them in a little bit, that are effectively lists. They might have fancy names like Tibble, or if you're doing a regression model, you may get this LM object. They're all lists at a base R level. And they hold many, many different things. They don't have to have a strict rule about what's in them. So that's the difference between lists and vectors. I hope that helps. And what map is requiring you to do is pass in one of these two. It wants any kind of collection that it can iterate over, be it a list or a vector. Okay. Okay, thank you for posting the more reading on the lists versus vectors. Okay, so I covered the first part of what goes at the beginning of the map function. The second part, and you may not need these types of output specifiers as much, but they are really, really useful. So by default, map by itself will return a list. That's the same with map2 and with pmap. But you may want to return one of these things, one of these vectors, things that are all the same type. And map provides some really handy ways to just take the output of map and do what's called a coercion, turning it into a vector. It takes the place of these functions that similar style names, but they're you need to append an underscore and then a shorthand for the type you want to output things as. So for example, map underscore character will do the same map as if you were doing map on its own, but it'll return a character vector at the end as opposed to a list, and requires that your output of the function is a character every single time. Map underscore chr will get cranky if you're trying to output a number or something that it can't coerce to a character, and you may get an error. But to illustrate this, I wanted to just look at that example from above. I was calculating an average across 3 different values, and it returned this thing I called my.calcs. But mean, the mean function, it's really returning a floating point number every single time. A more practical function to use, maybe a stricter function to use in this scenario, would be something like map underscore dbl for double, map double. And when you run map double, the input doesn't change. It's my list again, it's mean again. The output has changed, and it looks a little bit different than what was output before. And if you've worked in R for a while, you might understand what the difference is. MyCalcs is a list, and this $sign kind of shows you the named items in the list. Excuse me. MyCalcs2 is a vector. And it may not be apparent. I can generally tell based on the way these things are printed. That's not the most intuitive way to see the difference. The strict, like under the hood way to see the difference would be to call base R's class function on each. It'll tell you that my.calcs, the first thing I ran is a list. And the second thing, my.calcs2, is, it says numeric. It's really a numeric vector because there's more than one number in it. It would print out numeric if it was a single number or many different numbers. So that's kind of a quick look at the suite of functions available to you in purrr. Are there any questions? I can pause here if this has maybe lost anybody before moving on. We're going to move on to something with real data in a second. Or I could save questions for the end. Maybe that would be a little bit easier. So what I want to outline here is how to use purrr in data analysis, data manipulation, really. And I want to cover kind of what I call like a workflow for using purrr. It's a way to use the functions I've shown above in common, you might call it like a ETL type pipeline where you're taking in a bunch of raw data, manipulating it, and then ending up with a clean data file. And I don't know if this was like the intended use of purrr, but it shines when you have to do stuff like this. And I think as a journalist personally, these are the examples that have resonated with me because I am, trying to bring in a bunch of different data files, organize them, put them together. And I think there's a real use case for using purrr to do certain kinds of things. So I mentioned earlier, I hope everyone has like a basic knowledge of the tidyverse. We're just going to go over, I won't cover how to do these simple tidyverse things like reading in a file, manipulating columns in a tibble using this mutate function. And we'll get into kind of how you use purrr functions alongside these things. So in this folder, which you can feel free to clone and run the script later, I think I have to clean up a few things, which I will do after this class is over. I have kind of outlined a task I run into in journalism all the time, which is where I have a bunch of CSV files for yearly data separated. It could be the case that they each have like a year name .csv, and they're all of a similar format. So the data I'm using here, perhaps people here are familiar with, it's the Gapminder data. You might be familiar with Hans Rosling, who popularized this data, doing these really cool data viz examples in TED Talks. It's an interesting data set, and I think I've learned how to do various data manipulation tasks using it. And so I've outputted in this folder called data. And so for each year, there's a file, and each file has a country, a continent, life expectancy, population, and GDP column. And they vary a little bit. The countries are the same, but their values change. You can see Afghanistan's life expectancy went up in the 5 years between 1952 and 1957. So I'm going to talk about how to use purrr in a workflow to bring all of these data files together, which will hopefully make some sense about why you could use it in your workflow. So for reading and writing files, this is another library that comes with the tidyverse reader. There's a read CSV function. We can just take a look at one real quickly using read _CSV. I'm not going to save it. I'm just using it for the purposes of printing this out, just seeing how R handles it. Reader by default will guess the character types, and it kind of prints out what it's guessed. And then I haven't saved it in anything. It's just printing out the data frame. We can kind of see it's read in everything as you would expect. Country is coming as a character column. Excuse me. Continent, same thing. And then there are 3 double columns or floating point columns at the end. So I want to talk about how to bring this data set together in a tabular kind of way, sticking to, what I mean by that is sticking to like the rows and columns of a table or a spreadsheet. There are many different ways to do this exact task. I generally like to work in the tabular format because I think it keeps things organized. Now, I'll show you what I mean by that. So I'm going to start by just asking for all the files in the data folder. There's a handy function that does this, list.files. It'll tell you, if you give it a folder name like data, everything that's in there. There's 12 files in there. It looks like it's picked up all of them. And I'm going to put this in a tibble, which is the simplest way to create, or I shouldn't say the simplest. It's one way to create this, to start with a tabular format. This creates a one column tibble or data frame or table, whatever you want to call it, that has all of these file names. I'm further just going to append data at the beginning of it, data slash at the beginning of it. That by default, list files will just list the file names and not the source folder they came from. The source folder will be important for actually reading the file names. So when I run that, I get, again, this one column tibble that has the 12 different file names. And now we're going to jump into purrr and how to actually use it in this kind of workflow that I'm talking about here. So we're going to go use map, and we're going to take as the inputs everything in this column one by one. And as the output, we're going to ask for what comes out of read underscore CSV. So I ran one read CSV right here, and I can easily change it to say, okay, give me 57, give me 62. And what we're going to do here is replicate that process of reading in these file names one by one and putting the result alongside the file name in R. So I'll run this and explain it a little, explain what I've done here a little bit. So alongside the column that had the file names is this new column, which I called CSV. This is just using the mutate function. You give it a new column name to start with. And as the first argument, I said before, map requires a collection of things. I've passed fname. Fname inside a mutate function, let me back up. Inside mutate, the dplyer's mutate will know the column names as they exist in the tibble. So you just have to call them by name like this. You don't have to say, files $fname or anything like that. The names are available for you to use right away. And so it's taken this atomic vector, a character vector. It might be a list, actually. I don't know, but it's a collection of things. They're all characters. And it's going to pass them one by one into read CSV. So just like I was, putting file names one by one in here, read CSV is going to grab each fname and read them one by one. Furthermore, I didn't cover this earlier, another thing about map is that after you call the function name, there are a bunch of optional arguments. You almost never need to use them, but basically anything that read CSV might need, and I'll bring up the help for read CSV right here. If you need to pass anything to one of these other arguments in read CSV, you can pass it as an argument to map after the function name. So I mentioned earlier that read CSV does this thing where it prints out the column names on every single read of a file. If you're reading in many files, this could get a little bit annoying. I'll show you how that works. If I just comment this part and read this in again, read CSV has read in 12 files and it's printed out 12 column specifications. The way to turn off the printing of the column specifications is just to tell read CSV what the columns are ahead of time. It's nice that you can take this column specification and literally just copy and paste it up there. That's kind of how these functions were designed to work. So I've just copied the column specification, put it up there. Read CSV stops any guessing. It doesn't print out 12 different things. It's passed as an extra argument to read CSV as a constant argument to read CSV, as opposed to the file name, which is changing on every iteration. And we get this. And what I like about tibbles, as they exist in dplyr, is that the printouts are really helpful compared to what exists in base R. For one, you can see right here, right after the column name, you can see the type of column. Fname was a character column. That made sense. And CSV, what I called CSV, I could have called it whatever right here, is a list. And this, I think, is a really powerful feature of using purrr in this workflow. We've created what's called a list column. A list column, you might think of columns as just being strict values. They are characters, or they are integers, or they are floating point numbers. But they can also be lists, and the lists can have, like I said earlier, lists can have whatever in them. In this case, each cell inside this data frame is holding a tibble, or I think special table data frame is what this shorthand is. This shorthand is really useful also, and this is all in the printing of tibbles. They kind of optimized it for readability. What this is telling me is that there's a 142 row, 5 column data frame within this cell. And there's another one here, and there's another one here. You can't really see what's in there until you peek under the hood. And you can use basic R notation to traverse a list to figure it out. So I'm going to ask here quickly for files.read, the data frame, the column called CSV, and the first item. CSV is a list, so I'm going to ask for the first item. And here we can see this is a tibble. So this is what is inside this thing that is printed out as spec table TBL DF 142 by 5. It is the same thing as 1952. It is the same thing that we got when we just printed out readin data /1952.csv. And I think this is really powerful to be able to maintain your file name alongside the thing that you've read in. And this will prove useful in a second. I should have mentioned this earlier. The individual files do not have a year column alongside them. So if you were to read them all in and stack them all together, there are many different ways to do that. You would lack the year column. So I think another benefit of doing things this way is I can preserve the year column. It's in the file name. I can preserve the year, jam it onto the data frame that's been read in, and get the data set that I need, which has a year column plus the 142 rows for each year. Let me just check the chat real quickly. Let's see, this is pulling out. Yes, data table is a great package. I don't know data table, but I believe it is much faster to use. I need to learn that one day. Okay, cool. So we now need to move on to get the year column, kind of stack the data together. So what I'm going to do is I'm going to, this currently exists, the years in fname. I'm going to take a few steps just to clean this fname column. I'm going to take out data /, I'm going to take out .csv, I'm going to turn it into a number. Just taking out those things won't make it a number, it'll still be a string. And then we're going to use this function, which I believe is in tidier, called unnest. We can just look at the data after I get rid of, after I do the little bit of data cleaning on year. I have a numerical year column, and the data frame is still there. And there are 2 R functions for going to a data structure like this and getting out of a data structure like this. They're called nest and unnest. What we have right here is a nested data structure. It has a list column with data frames inside of it. That's nested. What we would like, if we want one full data set with 142 rows, or 142 times 12 rows, is to unnest this thing. And there's a function that just does it for you. It's called unnest. You just have to give it the data frame that you're working on, which should hopefully look like this, and the column that you need to unnest. You need to kind of explicitly call this, this column. So I'm going to run it right here, and we'll take a look at it. So now we've gotten a 1700 row tibble. What unnest has done is taken this year column, it's attached it alongside the 142 row. It was a 5 column data set before. We've ended up with a 6 column data set as a result. So it's put the year function, it's placed it alongside every single value in this table, and then it is stacked together the data frames. And I really like this feature that it preserves, information. We'll repeat it alongside rows. Sometimes you may not want your data values repeating if you're working in like a relational format where you're trying to keep repetition down. But oftentimes you do need something like a year value to exist over and over again. And unnest kind of just does all the work for you because this workflow is part of how Tidyverse has imagined people will work, which is, you nest things sometimes, then you unnest things. So that's kind of one workflow I wanted to talk about. Another one I wanted to go over real quickly, I think we're doing well on time, is to do this really common thing that I feel like I need to do a lot as a journalist, which is to generate many different plots. Sometimes I have a bunch of different data values, for various like neighborhoods in LA. And I would like to, for the purposes of exploration, to look at a chart for each neighborhood. And I think a purrr workflow can really help for doing things like this. So we have here, in this Gapminder data set, a bunch of different countries. I'm going to go through an example where, say you wanted to look at a plot for each country, looking at its life expectancy over time. We have a year column, we have a life expectancy column. Let's try to generate the same plot for many different countries over time. For simplicity's sake, I'm just going to do 5 countries, but you could easily do this for as many countries as you have. So I'm going to take this code, put it over here. So I'm going to start by kind of, we just unnested something. I'm going to look at how to nest something instead. So we ended with this thing called full data. What I want to do now is create a nested data set that has the values for each country. Previously, we had in this files.red, we had a nested data set that had the values for each year. Here's how you can do a nest pretty quickly. There are a couple ways to do this. Excuse me. I like to call the group by function, which creates these groups on the key that you provide. I've just given a country. And by calling nest, you get the nested data structure. Like I said, for the purposes of this example, I'm just going to do 5. So I'm going to quickly ungroup it, or it's going to be tougher to chop off 5. I'm just going to pick 4 random ones. So let me run this again. So it's the same 5. I set the seed, so it would be the same 5 countries each time. It's picked Jordan, Togo, Ethiopia, Botswana, and Guatemala. And so we're going to just create a plot for each of these. Here's how you can do that. We're going to create another list column, and this one's going to be a little bit different. This one is going to, it's going to take this data set, which we can look at one of them, by country, $data, 1. And this corresponds to the first item in there, which is Jordan, which is in Asia. And here's the life expectancy column for Jordan, the population, the GDP. What we're going to do here covers another kind of way you can work in purrr. I mentioned earlier, you might want to write a function ahead of time that outlines everything you want to do, or maybe you have a function like read CSV or mean are the 2 ones we've used already. They're named, they exist, they're in packages, and you just pop the name at the end of the map function and you can use it. To make a plot, there's no function that will make the plot for Jordan for you. You kind of have to make something a little bit custom to serve your purpose. And one way to do it would be to write a function ahead of time. Like I said, you kind of have to have some forethought when you do this, that will take the correct inputs and then provide the right output. What purrr provides is a way to do inline functions. I believe these are also called anonymous functions. And they are pretty easy to use once you've grasped the peculiar syntax. They start with a tilde, and then the function definition just goes from there. It will return anything that comes after the tilde. You can't do complicated like 3-step stuff here. It's strictly you write the tilde and then anything that comes after it will get returned afterwards. And furthermore, these purrr functions provide a lot of shorthands. Always, in the case of a map, .x will be the first argument. In the case of a map 2, you'll have .x and you'll also have .y. In the case of pmap, the arguments are a little bit different. I can cover that at the end with time, hopefully. But generally .x and if you have a map 2, .y are available to you. And .x will basically be whatever you pass as the first argument. So I'm going to take this data, this tibble, which is the same for every country, just with different values. And I'm going to send that into a ggplot function. I'm not going to cover ggplot. Maybe you've used it a little bit before. I really love it. I use it all the time to explore data. You start a plot by calling ggplot. It takes the data set as the first argument. It takes some aesthetic specifications for your, I guess if this was more literate, you would say, this is your X, this is your Y, and then you have to give it a geom, the thing you actually want represented on the plot. And I'm just going to ask for a line. So if we look at this, the printout I find again to be really helpful. It's told us we have a list in this column called plot. It could have been whatever I wanted it to be. And it says this is something called a GG object. And to look inside of it, I can just call plots.plots. I can call plots.plots, or sorry, not plots.plots, plots$plot. I can ask for the first one. In RStudio, by default, RStudio will put a plot in this pane called plots. This may be in a different area of your RStudio panel. Or I can ask for all of them by saying plots$plot. And it's telling me here that it's worked on 5 different things. What it's done is it's printed out 5 different plots here. And they all look like they're increasing with one that has a huge drop in it. And this is a really simple example. It's pretty easy to tell which is which looking at this. But I wanted to show just a slightly more complicated example. Something that would be a little bit nicer would be if we had the title on top of each plot. And this, I did this example to show a map 2, which we have not covered yet, a multi-input map. So I've changed this call a little bit. I've put country, which is the column in this data set, as the second argument to map 2. I've bumped the function call to the third argument here. You can compare the function calls here and here to see the difference. And I've added a line, which is the title, ggplot's title function, and I've given it .y as its argument. .y in this case is country. One by one, the country name will get passed. So map 2 is operating pairwise. The first one will take this data set as its .x and Jordan as its .y and pass it to this function. This, the second line will take this data set and Togo as its .y and create a new plot. And we can take a look at this. And now, if we look at the plot, if we look at the 5 plots, they have names on top of them. So this just serves to show how you can use the map 2 or the multi-map, the pmap, I guess, to take arguments from your data frame or tibble and move them along into a plot function. And again, what I like about this is it kind of keeps things organized. Your plot is alongside your data, is alongside the country name. And I don't know, for organization purposes, I like it a lot. The last example I wrote, which I'll just cover real quickly, is kind of how to save these plots. You may not want to just look at these things in the RStudio panel all the time. You'd probably want to save them as a PNG or a PDF, what have you. There also exists a suite of functions within purrr that are not called map, but are called walk. There's really only one difference between map and walk. Walk returns nothing. and is helpful when you don't want to save the output and use it again. This example kind of serves to show how you could use a walk to save your plots. Also, because this, saving a plot, I don't really need it to be a column alongside the 3 columns I've set up already. I just need it to run the process, save the plots, finish, do nothing with it. I've kind of done this outside the tabular structure, and I've been very explicit about what I'm passing to walk. Before, the maps were inside of mutates, and it kind of knew the column names. I didn't have to say plot $data, plot $country. And again, I'm using an anonymous function, which will then call ggsave. You give it a file name. In this case, I'm pasting .y, which is the country name, in between plots and PNG. And .x is the plot object itself. ggsave needs an actual plot object, which is a list, which has all sorts of stuff within it. And if you run this, this is my folder over here. You can get your 5 different plots output. I did this just to show, if you're wondering which one is the country that has the huge dip, it's Botswana, which has dealt with an AIDS epidemic for a really long time until the present day. That's / life expectancy there. So that's it. I'm right at time, but I wanted to save some time for questions. I listed some more purrr resources at the bottom that may help you. I hope this was somewhat easy to follow along with. I think I have to clean up the script a tiny bit, but I will update the repo here. But that's it for what I wanted to share.
This is great, and great, and really good timing too. I guess we do have time for if anyone has like maybe 2 questions.
Happy to take it.
I have a quick question. This is like, I really love this to do it with ggplot, and it'll make like, because we have like a lot of county controls, so we'll get like 88 different spreadsheets, sure, which all have different column names, so that's a different story.
Oh yeah, sure.
So like we want to make one of like each county, so that I'll do that. But then like when I'm scrolling up and down, it's like really slow to like click on each one. Is there like a logistical way to do that?
What exactly is slow?
So like I'll have an RMD file and I'll say, go through every county and pick out, whatever. And it'll pop up with 88 different graphs there, which is
in the pane in RStudio.
Yeah.
Now RStudio, it is trying to be convenient, and it gives you that viewer so you can look at things really quickly. There is like an efficiency drop off as more and more things, or I've noticed this, I don't know this to be a fact, there is an efficiency drop off as more and more things go into that viewer, and it becomes harder to say go back in the viewer, which I don't know, maybe someone here knows a way around this. This is why I like exporting the plots, and which is why I wanted to show this export example. I'm often looking at like 50 plus counties in California or hundreds of neighborhoods in LA. And it's after looking at 2 or 3 plots at a time, I'm not gonna hit these arrows to go back to look at hundreds. I think the real upside is exporting. And you can use, I'm on a Mac right now, but I've been on a Linux before, and I like to literally just like bring up the preview and hit the arrow button and go one by one and look at things. So I would be in favor of exporting in a situation like that and not relying on the R viewer to navigate through tons of plots. This example is 5 plots, but once you get to like 10, I mean, that starts to be too much for me. So I'm always in favor of just kicking them out. PNGs, PDFs, what have you.
Well, Ryan, thank you so much for taking the time and kicking this off for everyone.
Yeah, no problem. Thanks everyone for stopping by. And I am pretty easy to find. I'm on News Nerdery in this channel where Andrew helpfully came up with the concept for this conference.
Yeah, absolutely. If anyone has questions for anyone else throughout the rest of the day, like we can just thread it in the News Nerdery, our channel. All right. Yeah.
Yeah. Cool. Sounds good. Well, thank you everybody for stopping by. Wow, there were a lot of people here.
And this is great. I mean, I didn't really like promote this at all on social. It was just like really just word of mouth, and all these topics are like what all y'all voted on. So yeah, so this was great. Next, we've got Lenny Bronner, and I'm going to just go ahead and let him take it away and introduce himself. Lenny, you're muted.
Thank you. Sorry about that. It's only been a year of using Zoom and still. Can you all see my screen? Good. So I'm Lenny. I'm a data scientist at the Washington Post. I mostly work on elections related stuff, but I also sort of help out with modeling when it comes to sort of newsroom needs. And that's sort of what I'm going to be talking about a little bit. So practical models that we use in the newsroom. There's a whole variety of models that you can use in journalism or like that are used in statistics and can be used in journalism. But I'm specifically going to be talking about linear regression and logistic regression. The reason I'll be talking about those is, well, mostly Andrew specifically wanted to know about those, which is, and it's a good thing. And they're used very commonly and they're really helpful. So that's what I wanted to, that's what I wanted to talk about. So sort of a little bit of a background, sort of regression in general is a measure of relationship between different variables. And it's useful for two different things in general. It's useful for inference, which is the measure of the relationship, and that's sort of the question we ask with inference is how accurately can we estimate the relationship between these variables. And it's also useful for a second thing, which is prediction, which asks how accurately can we predict the outcome variable that we're interested in. And like I said, I'll be talking, I mean, there's many different kinds of regression, but I'll be talking about these two specifically, linear regression and logistic regression. And the difference there is what kind of outcome variable we're talking with. So in linear regression, it's a continuous variable. So something on the number line, basically. And for a logistic regression, it's when your outcome variable is discrete, sort of a yes or no, and like discrete and binary. So a yes or no sort of case. At the bottom here, I sort of have the two, sort of generic formulas for regression. The first one, the top one is a linear regression, where we're saying that our outcome variable y is sort of equal to some other variables, x1 through xn, times some coefficients. And for when we're doing inference, we're trying to estimate these coefficients, beta 1, beta 2, beta 0 through beta n, and saying how good our predictions are, like how good our estimates are. Versus for prediction, we're really just using this formula to predict y on sort of unseen data. And this is the formula for logistic regression. This is the probability of x. And so you can see here within the exponent at the bottom is sort of the same formula for linear regression. I'll be moving back and forth between them a little bit, but the reason I put them together in one slide is because I sort of like to think about them as sort of very similar, just, for a different kind of outcome variable. But sort of in general, we're trying to do one of two different things, which is either inference or prediction. And I wanted to talk about a specific example, which is sort of the practical aspect here. And we've used this model in stories before, and not only us, I know The Economist has, for example, too. But what we're trying to do is an individual level voter model for Donald Trump. Basically, how likely is it that someone would have supported Donald Trump? And like I said, there's sort of these two questions we could ask. The first one is the inferential question, which is which demographic features are associated with voting for Donald Trump? And then there's the prediction question, which is how good is our model at predicting whether someone would have actually supported Donald Trump or not? And in this case, what we're going to use is the cooperative election study, which is a big survey that comes out every year, but specifically in election years, and they ask 50,000 people a lot of sort of demographic information and also who they voted for. And in this case, we'll be using gender, race, and age, and a couple other variables to sort of predict how likely it is that someone would support Donald Trump. And then we apply it to the voter file. And in this case, I'm using the North Carolina voter file because that's sort of freely available to download if you sort of wanted to replicate this yourself. Yes, this is my big takeaway, which is don't do inference if you're writing a news story, unless you're working with a subject matter expert. Why? Well, everyone sort of knows that correlation is not equal to causation. And when you're writing a news story, you will want to write about causation. And you will really want to write about causation. But you will know that you're not allowed to do that. And so you're going to be paying lip service to why you're not allowed to do that. You'll have a line in your story that says, we know that we can't make any causal statements. And then 5 paragraphs in, a causal statement is probably going to sneak in because you're writing a news story and you really want to do that. You really want to tell a story, but you can't. But I know what you're thinking. You're like, fine, I get it. I can't make a causal statement. but I can interpret my correlations, right? And if I'm really careful about what I'm saying, I can still sort of use inference and do regression. But I want to show you guys something like an effect called omitted variable bias, which shows that you also have to be very, very suspicious about the correlations that you're seeing. So what we have here is we have our script, and we have here data from the CCS. So this is sort of, I've selected out a bit, but basically these are 50,000 responses or so, a bit fewer, 43,000 responses, because I've sort of cleared out ones that don't work so well for us. When we have sort of the gender and the race and education and an age bucket that someone falls in, what state they're in and their county, and whether they voted for Trump or not, according to this survey. And so say that we wanted to write the simplest sort of model that we would sort of start off with, which is we're trying to predict whether someone voted for Trump based on their race. And LM is sort of the R command for, LM stands for linear model. So this is like a linear regression. And so if we run that and we look at the summary, what we can see here, in the estimate column, we have sort of what is basically the correlation, or like the effect, the estimate for the effect, which is, if it's positive, someone, if they're Hispanic or Latino, are more likely to vote for Donald Trump. If it's negative, sort of the other way around. And what we have here is sort of information about like how big our error potentially is for that estimate. And then basically what we have here is our p-value. And I mean, p-values are obviously quite hard to sort of interpret or like, explain what they are in one sentence, but the way you can sort of think about it is like the estimate of the probability of how likely it is that this number here is incorrect. And as we can see here, we're very certain about all these numbers, incredibly certain, right? Like in a lot of science, a p-value cutoff of 0.05 is used, and these numbers are a lot smaller than 0.05. So our model is saying that it's incredibly confident about these estimates that we're seeing here on the left. But like these estimates already look a little bit strange. Like there's a positive correlation between being Hispanic and Latino and voting for Donald Trump. Like that already should sort of raise suspicions just based on sort of what we know about how the electorate works and sort of other estimates that you may have seen of the 2020 election. And lo and behold, if we run a more complicated model, in this case, we're using race, education, gender, age, and what state they're in, and we run the sort of the same basis for a model, suddenly this number is negative. And it's no longer statistically significant. But like previously it was positive, and our model was so sure that it was positive. It was so sure that it was positive. And like we run a more complicated model and suddenly it's not. And this effect that I sort of showed you here is called omitted variable bias. And it's sort of a real problem that, if you might not be a subject matter expert, that you might sort of run into. And in fact, a lot of subject matter experts actually run into this problem too. And I know what you might be thinking here, which is like, this won't happen to me because I know all the variables that are sort of relevant. This was a contrived example. Like, you showed us a model that only had one variable in it, and then you added all these other variables, and you're like, look, the effect changes. And it's like, but like, no, it will happen to you, and it might have already happened to you. And like, this is a very common problem. But one of the issues is that it's actually not the only problem that exists with regression. I'm happy to go into like more other ones, but it's like one that has a very specific sort of, I mean, you guys saw what happened in the model that I just showed you, right? The effect went from positive to negative. And our model was initially incredibly sure. So you can't even trust, the estimates, even when they're statistically significant. Can't even talk about the correlations in a way that you would want to, even if you're really careful and don't use causal language. So what can you do instead? Well, what I like to do instead is I do prediction. In general, for prediction, it's sort of easier to know whether you're doing something right or wrong. Obviously, there's a lot of things that can still go wrong, but it's substantially less fraud than sort of the inference aspect. And so in this case, here's another slide, sorry. The story that we'd like to tell is sort of what would happen if we reran the 2020 election, but everyone in North Carolina voted. And we don't need to care about inference in this aspect at all. We don't need to, like I wrote here, we don't need to quantify the relationship between race and voting preferences to understand this journalistic question, or even to answer this journalistic question. We can answer it using a predictive model. And so that's what I have in the code here. And the reason we can sort of get a better understanding of whether this model works or not is because we can evaluate the model. And there's many different ways of evaluating predictive models. There's like leave one out. There's like different ways of cross-validation. I've chosen sort of the easiest way of doing this, which is really a model, which is sort of a training and a test set, which means I sort of split my set, which is the CCS, the same data that we had previously. And I split it into two, a training set and a testing set. And this is really important, sort of an important takeaway, which is like when you're evaluating your predictive model, you really should try and, or like you really need to split your data. Either you're doing it through cross validation or the training and test set, because like, you know, evaluating how good your model is on the set that you're training your model on is not good. And can lead to like a lot of issues. And so that's what we're doing exactly here. So I split my set into two, one of which is of size of like 80% of the data, one of which is the training set, and then the sort of leftover is 20% of the data. And I'm training a model here using the state, like I said, age, race, and gender. And you might notice that I'm leaving out education. And the reason I'm leaving out education is because I'll be later applying this model to the North Carolina voter file, and that unfortunately doesn't include education. And as you might see here, in this case, I'm using GLM, and I have here family binomial, and this is sort of R for a logistic regression. So previously I was sort of using a linear regression just to sort of show this issue with omitted variable bias, but now I'm, you know, running a logistic regression. And so we can run this model, and then we sort of predict on our testing set. And type response means we're receiving out the probability, and then we can evaluate this model. And here we're evaluating the accuracy. You know, there's many different metrics for evaluation. It's sort of when you're running your own models, it's important to think about how you want to evaluate the model, what kind of number that is, like what kind of metric is the one that's useful for you. Accuracy is sort of a basic one, which is how many you get right divided by how many you're sort of using, how many are in your testing set. And so I can run the predictions, I can calculate the accuracy, and the accuracy is about 0.66. If we added in education, the accuracy would go up quite a bit. I mean, it's not vastly surprising that education in the last election was pretty important in terms of determining who someone voted for. But this is sort of a more basic model. And so now, you know, imagine that I tested different kinds of models and I sort of evaluated them using what I just described, you know, evaluating these models on data that's outside of my training set. And I've decided this is the model that I'd like to use. And in fact, having run models like this before that are substantially more complicated, this is actually pretty good. I mean, adding education would do a lot better. But models without education, excuse me, you know, you can only squeeze sort of so much information out of these surveys. And so we rerun the model using all data, and we can take a look at the coefficients and sort of the p-values. But like I said before, you know, don't put too much stock into these because our model is only sort of so good. And then I have the North Carolina voter file here. I've sort of subsetted it a bit to make it sort of easier to understand. But we have sort of very similar information. We have the voter registration number for everyone in North Carolina, state abbreviation, because that was part of our model. We have race, gender, age, and whether they voted in 2020. And what I'm doing here is I'm running these predictions for only the people who voted in 2020 to sort of see whether our model is good enough at sort of figuring out, you know, who voted in 2020, or like, you know, can we sort of rediscover the actual, you know, results that happened in 2020. And as you can see here, the actual results in 2020 was Donald Trump received 49.93% of the vote. And if we run this model, we get, I think, incredibly close. So the model actually does pretty well in aggregate. We can see here that on the individual side of things, like I showed you guys before, the accuracy, you know, the model might not be so good because on an individual level, you know, we only get it right 66% of the time, but sort of in aggregate, it does a pretty good job. Which makes us confident sort of for the next part, which is like, what would happen if we rerun the 2020 election and everyone in North Carolina voted. And so now we're not subsetting the voter file anymore. We're sort of running it for everyone. And if we run this, we can see that Donald Trump would receive approximately 47% of the vote, which would probably be enough for Joe Biden to have won the state. I mean, this isn't two-party vote share, as you guys can see. That, I mean, Donald Trump won in 2020 with 49.93% of the vote, so Biden would probably win. But as you can see, it wouldn't be a landslide. I mean, the model sort of realized that North Carolina is a swing state, and like, even if everyone voted in North Carolina, the results wouldn't be overwhelming. But this is also a product, and this is sort of something that's quite interesting. You guys can see that I have a cutoff set of 0.471. That's of my probability cutoff. And I can talk about how I sort of got that probability cutoff. Everyone who received more than that has a higher percentage of that to vote for Donald Trump. I sort of assumed voted for Donald Trump. And then, like I said, if there's questions, I can sort of go into like why I decided to use this cutoff and not 0.5. But if we play around with the cutoffs a little bit, if we set it to 0.5, we can see that suddenly the model thinks that Joe Biden would win pretty overwhelmingly. So there's a lot of people whose probability of supporting Donald Trump is between 0.471 and 0.5, which is really an indication of like the fact that there's a lot of uncertainty here. I mean, like I said, North Carolina is a swing state, and there's a lot of people for which the model sort of has, might not have the best job figuring out, how well, whether they would have voted for Donald Trump or not. But sort of the flip side of that is if we set the threshold down to 0.4, we can see that Donald Trump would probably win. I mean, he would receive, or he would definitely win. He would receive 56% of the vote. But there's definitely like there's a discrepancy here between how well Joe Biden could have done if everyone voted and how well Donald Trump would have done, which shows that potentially Joe Biden would have had a bigger upside here than Donald Trump. But this is sort of other ways you can sort of check for the robustness of your model, sort of play around with different parameters a little bit and see what of effect they would have on the model and see whether it makes sense to you, whether it sort of makes sense with your understanding of the problem setting at hand. Yeah, this is sort of the example here. And then I sort of wanted to point out that we have in fact used a very similar model in a story before. How turnout would have increased, would have changed. And we ran this model on the same survey in 2016, not in 2020, to see what would have happened if everyone would have voted in 2016. And I'm working on a story right now where we're using a similar model for the 2020 election. Not this exact story, which is how would have everyone voted, but we're trying to get an individual level estimate for everyone, how likely it is they would have voted for Donald Trump for sort of something different. And sort of the last thing that I want to mention is that don't forget to mention the caveats in your story when you're sort of using this kind of modeling. There are a lot of things that can go wrong, even when you're doing prediction, even though I would say, like I said, I think it's generally less fraught than inference. But basically your model might be overfitting, which means that your model might be too close to what the training set is saying. You might be extrapolating outside of your training set too much, which is the examples that you're trying to work on are very, very different to what you've trained on. And it's also important to mention sort of the things that your model are assuming. And in this case, the big assumption of this model is that people that are demographically similar, the people who didn't vote in 2020, but are demographically similar to people who did vote in 2020, would have voted the same way as their sort of the people that they're demographically similar to who didn't vote. And there's a lot of reasons to think that might not be the case. People who don't vote are in many ways quite different from people who do vote, people who choose not to vote, as we kind of saw in the 2020 election with a record high turnout. And so like this assumption is one that's fraught, and this assumption is one that, it's always important to mention the assumptions that you're doing in your stories when you're doing modeling. Thank you. Any questions?
Looks like there's some, Sarah, do you have, if you want to ask the question out loud, I see the question here in chat.
Oh, sure, sorry. Is my microphone on? Yeah. I'm just confused about how the model is actually working, because if it seems like, and I'm just making sure I understand what you're doing, if you're using 80% of the records to train it and then changing the cutoff from 50% to something lower, aren't you kind of forcing it to add up to what you want it to add up to?
So I retrained the model on all the examples here. So the model that I was actually using when I was applying it to the voter file was run on all the examples.
Oh,
The 80-20 was just to sort of evaluate how good the model is.
okay.
But for what it's worth, if I change this to 0.5, the number barely changes. It changes to the third decimal place.
Okay. All right, thank you.
All right, unless who's next?
Hey,
Or question.
hey, Lenny. So this is really cool. I wondered about the cutoff, right? So establishing this threshold, is this kind of from, reporting, talking to political scientists, kind of trying to figure out what these, kind of who those fence sitters are and what they represent, as opposed to, looking at some of the kind of coefficients and outputs of your model to determine what the kind of uncertainty is?
No, it's actually part of the model training, which is what's actually happening here when I calculate the accuracy is it's calculating the accuracy at many different cutoffs. It's sort of what would happen, how good would our model would be if we set our cutoff at 0.1%? How good would the accuracy if we set it at 0.15%, at 0.2%, that kind of stuff. So I can show you all. So these are the different accuracies at different thresholds. So I forget exactly in what order it is, but this one might be like, if we set the accuracy at 0.1% here, it's at, maybe 0.15%, 0.2%, that kind of thing. And then I choose the accuracy, then I choose the cutoff that maximizes the accuracy.
Okay, that's awesome. All right, I guess that's resonating, because I would do something for like topic modeling where it's trying to estimate the most kind of accurate number of topics using something similar, right? Where you test against 50, 100. Okay, cool, thanks.
Lucia, you had a question?
Yeah, I just wanted to see, how do we get this national data set, the CCES?
Yes. I will add the link to the code. If you just Google like CCS, or CS Harvard, it's like a Harvard data set. Yeah, I'll post the link to it.
Cool, thank you.
And it goes back, many years. They have many years of this. It's pretty cool.
Yeah, it looks awesome.
Lenny, so if based on like the results of your recent model, how would you then translate those numbers into a story, like as a nut graph or whatever sentences it would require?
Yeah, that's a good question. I don't know. I like exploring sort of different scenarios. Like, your model is one model of the world, and you can say like, what would happen? What would this model think? I think it's important to sort of clarify that this is not what would happen. This is like, what does your simplified model of the world say would happen if you sort of played around with sort of other parameters. And then, in this case, sort of like, yeah, we looked at how many potential voters. This again, the story that actually came out so far was one from 2016. So we looked at like how many potential voters would have voted for Hillary Clinton but didn't. How many potential voters would have voted for Donald Trump but didn't. I realize this doesn't really answer your question, but I don't have a good answer for that question. I think it sort of is very much a case-by-case basis kind of thing. I'm sorry.
Sharon, you had a question?
Yeah, I was curious if you do any kind of modeling looking at campaign contributions versus election results or anything with campaign contribution data.
I have never run models with campaign contribution data. I've done some unsupervised stuff with campaign contribution data where you try to match campaign contributions when like the names or the addresses are slightly off and things like that, but you want to figure out whether they're actually the same person. I usually do that through like unsupervised stuff here. But I've never actually done anything in terms of like regression and campaign finance.
Yeah, I'm kind of interested in that in local elections where there's like no polling and it's really sort of difficult to see, looking at like number of contributions and whether that correlates. I was just kind of curious.
Yeah, that's a good question. And I also, I would actually, I assume there's political science research out there on that, I think, I would hope. But that might be I would hope that someone has tried this, and so there might be something out there. But unfortunately, I've never done it myself.
Thank you. This is really interesting.
This is kind of a meaning of life question. I thought it was really fascinating, like the Hispanic, influence kind of peters out once you add in education. Like, is there any point where you can say, okay, I have 5 variables. So, there might be a causation with X, Y, and Z.
Well, unfortunately not. I mean, even if you solve the omitted variable bias issue, you still can't make causal claims. The omitted variable bias is sort of the issue with even interpreting the correlations, but making causal claims is sort of, you need, the problem with the causal claim is that you don't ever have the counterfactual in your model. It's sort of hard to, you can't evaluate it. Whether you can sort of think that your omitted variable bias went away. I mean, that's why I think it's so important to work with subject matter experts who would have a better sense of like, what are the potential things that might have influence? What are the variables that might be relevant here? From what I gather, sort of on the like predicting whether someone would have supported for Donald Trump or Joe Biden, it seems that these features or covariates, demographic features plus maybe education does do a lot of the explaining. So there might not be very much beyond that. That sort of you might not run into issues beyond that. You could say that there's maybe county level changes that might have an effect. Demographic groups in particular counties might be different from demographic groups in other counties, even though. And
then I guess sort of the corollary to that is we don't really know if education has an effect then, right? There could be additional variables or why people get an education versus not in the first place.
Absolutely. The omitted variable bias problem never really goes away, unfortunately, which is why my advice is, if you're trying to write a story, unless you're working with someone who really knows this data well, like stay away from inference, because there's sort of a lot of places where it can go awry.
So a question about process here. My sort of half-trained fumbling in the dark approach to regression is usually to start out by sort of throwing the kitchen sink at it and then paring down, or throwing the kitchen sink of variables in, or making a hypothesis for, well, I think these 5 variables are significant, and then so these two approaches, right, throw everything in and then remove the ones that aren't significant and keep fiddling, versus make a hypothesis and then try adding and subtracting and seeing what it does. Are those? Can you comment at all on the best way to choose the variables that go into your model?
Yeah. So if you are really set on doing inference, then, well, the problem with the kitchen sink method is that, you may think you have all the variables, but you probably don't have all the variables. Like your data set is probably not exhaustive. The likelihood that you have all the variables that explain whatever effect you're trying to sort of get at is pretty slim, especially in sort of real world examples. So like I said, I mean, this doesn't solve the omitted variable bias problem either. In terms of like variable selection, if you're really trying to do inference, then you have to do the second approach, which is you have to start with an hypothesis for your variables and check whether they're statistically significant. Because if you do the kitchen sink method, you sort of, I mean, this is a bit technical, but you run into like multiple testing issues, which, we can talk about offline or something, but like, so you have to be a little bit careful there. In general, if you're trying to do prediction, but you're also trying to sort of pare down the number of variables you have, then it doesn't matter what you're doing. Then you can sort of play, you can try as many combinations of variables as you want. And you can sort of, just see which ones are actually good for your model, which ones actually improve the accuracy or whatever metric that you're interested in trying to improve. Did that answer your question?
All right, time for one more question, or we can wrap it up, or you can ask Lenny in the thread in the R channel. Anything else? Oh.
Yeah, feel free to, I'm in News Nerdery too. So, if you have questions, feel free to DM me or post in the channel.
Great. Okay, so we're going to take a break and we'll be back at 2:25 for some tidy tech stuff from Alessi when we're back. So we're just going to take a break and I'll see y'all at 2:25. All right. See y'all soon. Hey, Alessi, how are you doing?
Doing well.
Dealing with any cicadas, or are you still out of town?
No, they're not this far east in Ohio, so
Okay.
we are good.
Okay, well, I'm assuming everyone is kind of just coming back. We've got, for everyone else who is kind of lurking in the background, for the next, I guess, hour and, is it? Yeah, hour and 15 minutes. The next hour and 15-minute block is going to be about text mining and kind of an intro to working with maps in R with Aaron as well. So I'm going to just pass it on to Elizabeth. You can introduce yourself and talk about what you're going to talk about.
All right. Thanks, Andrew, for putting this together, for everyone, for being just such an awesome community, you know, on Slack and whatnot. I've learned so much by standing on your all's shoulders, and now, you know, doing stuff like this on deadline, which is awesome. Okay, so I'm going to talk text analysis. The links there you can see. I don't know why, but O'Reilly trusted me to like give a course, do it a couple times. And if you want to write a book for O'Reilly, not that I did, they want you to do a course first and then you write a book for them. So, you know, that's a track and it's cool. So that's where a lot of this is from, but you can imagine a lot of folks in data science and finance are really interested in using text analysis. So I'm going to share my screen. I'm going to go over to the README file. Okay, can everyone see this README file? All right. So I'm not going to kind of break down a lot of the the basics. Definitely not of once we jump into R. But so what I wanted to kind of touch on is, you know, unigram, bigram, trigram kind of analysis, like n-gram analysis. If you've seen things like the Google n-gram reader, right? And this idea of sentiment analysis too, right? So we're gonna get into that and every caveat associated with it. We don't need to clone any repos or anything. I just want to go really quick to inspirations, right? Kind of what set me off on this track, or kind of not running the other direction when someone asks, let's do a sentiment analysis of social media. And I say, whoa, hold your horses. It might not tell us anything. But where I had seen some great work is, you know, folks like Peter Aldis using stuff like the State of the Unions, right, over time, doing simple but very effective analyses of, say, the complexity of speech over time, right? So, you know, when someone suggests sentiment, right, or like, can we measure joy or negativity? You may want to say, well, hey, why don't we use something like the Fleisch-Kincaid score and measure the complexity of language? Wouldn't that be a little bit more interesting? And narratively, you can see where you could kind of go and run that by subject experts, because just as much as maybe you and I are allergic to just throwing sentiment at something, the subject experts are too, and they may be a lot more interested if you come at them with a lot of skepticism towards these tools. And so I'll show you those tools. But other things that are inspirational, you know, stuff like you know, the Times working with the Mueller report, kind of pulling out the biggest names in the report and how often they're cited, right? That's simple text analysis. That's literally just counting the number of those keywords. Candidates talking about Trump. You know, I love this idea of, look, the data set for this was candidate emails through the 2020 campaign. So could you amass a data set that would answer a question like, who's talking about Trump the most in their campaign language, right? Go out and get that, because the analysis toolkit is fairly simple when it comes to counting the number of times Trump is mentioned. This is from Boston Globe, arresting words. So looking at words involved in arrests. This may have been when Andrew was at the Globe. Arresting words, no. Okay, and so then I'll show you some of these things that I've done in looking at things like Antifa or the Dominion voting systems on kind of more fringe platforms like 4chan, and tools that I've used to do that. We don't need to kind of see how it's used. Crimson Hexagon, recently acquired by Brandwatch, out in, you know, marketing ad land. These kind of tools are very often used with varying levels of, let's say, accuracy. And then sentiment analysis. So let's all think of that as kind of like, the text analysis, kind of looking at literally kind of numbers of mentions in the most basic sense. And then sentiment may be, okay, how can we assign some kind of emotion to that word? But of course, as we all know with this language and others, it's open to interpretation, right? I did this piece, one of my kind of first most data-driven pieces that kind of got me on this. I was a science reporter, for years, and doing this kind of analysis, thinking about how you can apply these kinds of tools to questions of politics was an exercise and a lesson in measuring and then explaining to readers what false positives and false negatives are, right? So for instance, so the whole kind of thesis here is that even though Democrats were the party that were going high, right, to the 2018 midterms, they were actually going low, right, on Twitter. And one of the caveats there was, kind of like the screaming fire in a theater, right? If you're screaming fire on social media, it doesn't necessarily mean a negative thing, right? You can say that the crowd is fired up. That could be a very positive thing in politics. And so your sentiment analysis has to account for that if you're scoring fire as a very negative word, right? Fire, murder, kill, right? Depending on the language, the dictionary that you use. Okay, so what I'm going to do, since we obviously don't have too much time, is show you some code. So we can just like start running code. Okay, so over to here, and hopefully y'all can see this. Can you guys see my RStudio?
Yes, and it's nice and large. Thank you.
Great, perfect, awesome. Okay, so load these. So that's the second link that Andrew sent. But load tidyverse and tidytext. Hopefully you have those. And we're just going to talk about a few kind of basics of the tidytext package. The tidytextmining.com is it's the R book online. It's amazing, by Julia Silge and David Robinson. Amazing resource. I mean, besides them and then a bunch of amazing PhD students in network science and English taught me how to use this stuff. So the community is great out there. Okay, so the first thing we'll do is, if you'll pardon me, we can just jump right into it, is throw in a sentence, right? Store it as line, the object, and then call the object. And you should have, you may recognize this from testing out fonts. The quick brown fox jumps over the lazy dog, right? So the first thing I want to do, because tidytext, it's in the name, likes tidy formats, let's throw it as a tibble. There's obviously various ways that you can store these things in a tibble format, but I'm going to call it line tibble and I get to pull it. And so column name is value, and there's their sentence. So, and it took me a while to kind of figure this out. When I first time heard tokenization, I had no idea what they were talking about. So what a tokenized sentence is taking the component pieces of the sentence and splitting them into their parts, right? And so this is kind of part and parcel, the basics of doing an n-gram analysis. And of course, sentiment would be to split up and measure kind of what those words are that make up the sentence. So here you go. It's a sentence made up of 9 words. So using the tidytext function unnest tokens, you say, okay, pull out the words from the column value. So if this were like social media, if this were tweets, I would say pull out the words from text, right? Which I think is the way that the Twitter API gives you back the text of the tweet. All right, and then you call line tokenized, and I see it's a tibble like this. Okay, first thing I can do is count, right? Count the words. The is used to, so then you'll probably really fast at doing the kind of sorts, do a kind of sorted table of the frequency of these words. And I want to introduce stop words here. Kind of a funny name, stop words, but this is your thes, ands, other kinds of, you can actually inspect them right here. Other kinds of words that some academics will strip out of an n-gram analysis or any kind of content analysis of text. Now, and the reason I put this question here is there may be a reason you don't want to cut out a bunch of these, and you can throw it in the chat. But in this case, we cut out a few of these words. And if you change your anti-join to inner join, you can get a sense of the words, right, that were cut out, and the stop words lexicon and what it's done to kind of annotate what those words are. And don't ask me what these mean. I've actually never looked into what smart, onyx, and snowball are. But if you use anti-join, you will cut out of our sentence the and over, and then you'll get a kind of clean sentence with 6 words. All right. I know I'm going fast because I want to get to more interesting things than just that sentence. So let's go down to pulling in a speech. So if you have, in this case, this is a .txt file, right, with just the body of a speech, right? So you can do this. I mean, Peter Aldous did this with the State of the Union speeches, right? They were each stored as a text file. He probably did something like Ryan showed us and kind of, porting all of those text files or transcripts. You can do this with transcripts. You can do this with news article text. You can do this with any kind of number of files that contain text, and then kind of rectangularize them into a data frame using things like purrr. So this is just one speech, right? So I'm reading the file in, it's in this object, and then I want to put it in a tibble. And so one cell is one speech. So you can think about how you would want to amass your own data set of maybe every Trump speech from the campaign trail or every Hillary speech. And then we want to use this unnest tokens again, right? So, point to the object. Okay, value is the name of my column, and then unnest the words. So word comes prepackaged in that function, right? They kind of know that what we're looking for is, the tokens of one word long. And so once I run that, I have almost 6,000 words, right? It converts them all to lowercase, which can become an issue to deal with later down the road. But let's do a really simple thing and I'm going to kind of chain these all together using the pipe, but take my one speech that's in a tibble, unnest the tokens, count the words, and then glimpse it all at once. And so this, you'll start to realize why, in some cases, academics would strip out those stop words, right? And the to, of, we, in. We may be the most important of those top 5, but let's cut them just to give us a kind of quicker sense of what's maybe kind of more, narratively interesting of here. But, people, Americans, Tonight America Country, probably not too different from an Obama speech in terms of the top 5 words mentioned, right? Minus stop words. So you can obviously inspect these, kind of get a sense. We do a lot of analysis here at USA Today of, kind of let's just count up some words. Let's just see what's the kind of substance here before we try to understand the context around the words. It's helpful to kind of look at how many times a specific word is mentioned. So here's bigrams. So I'm going to run it first, but essentially, right, we are telling it, and this is all amazing. I mean, tidy text has this built in. Okay, point it to value and then ask it to pull out the bigrams. They have this kind of the other arguments within the function where, and this becomes important when you want to do more than just a bigram, but a trigram or I don't know what it would be called, a quadgram, a quintgram. You can kind of go up. But what this does is it kind of pulls out these bigrams and then counts them. And then I'm just saying, okay, well, let's check these out in the we are of the thank you. Okay, so that's interesting. Not really. It's got so many stop words up top that it's not giving me a kind of good sense of what the biggest bigrams, the kind of most important phrases were. Most important probably wouldn't be of the. So let's store it as a Trump bigrams object. And then I'm going to run something. This is straight out of the tidy text book. which is let's split that bigram into 2 words, right? Here's the separator between those 2 words, right? Find a bigram that's separated by a space, split that into 2 words, right? And then store those as 2 columns named word 1 and word 2, right? So word 1 and word 2, Mr. Speaker, Mr. Vice President. And then you pass that stop words list to each column, right? And you filter them out. It's a kind of a weird, and it takes a while. Like, I don't think I fully get it, but it works, all right? You're like, never taking a class from this guy again. He can't explain anything. But check it out. So now, after pulling out those stop words, I'm taking out any column, right? I'm taking out any row that had a stop word in it, whether it was in column 1 or column 2, right? So if it had the in it, goodbye. If it had and in it, whether it was in the first or second column, goodbye, right? So then that what's going to do is kind of move around your frame of reading the text of the speech to finding actually the most interesting phrases that are 2 words long, all right? And so I get things like MS-13, American people, North Korea. Suddenly I have something interesting, right? And I have something I can compare to past speeches. So you could kind of run this same thing on State of the Unions, right? And look across time what the kind of most frequently kind of, uttered phrases were. So speaking of, and we'll go to questions at the end because you probably have a million for me because I'm not doing that great of a job explaining this, but let's go to a bunch of speeches instead of just this one. I'm sure you have 10 questions you could ask that Trump speech. But if you pull in the State of the Union, so Peter, I think, put this up on his repo. And so everything's there, right, in terms of the link to the transcript of the speech, who it was, and of course the text here. So a couple things I want to do, right? Remember, if you kind of jump back to his story, one of the kind of visualizations was reading level over time, right? We may want to kind of preface that with well, let's look at length first. Let's look at the length of the speech over time. And so we've got a date column. We've got the text of the speech, right? Well, then let me do a simple thing. Using, right, the stringer package and using string length, I can calculate the length of that speech, right? And I'll mutate out a new column and put that in there, right? So I do this all the time with, for instance, big dumps of email files. So if I get through a FOIA a ton of emails, I pre-parse it using these kinds of things to kind of understand which are more interesting. And of course, which words I can kind of pluck out and find, or if I'm looking for a specific word in a dump of a gig of emails. Anyway, would love to talk about that if anyone has tools to share for parsing Outlook email boxes. Okay, so what I did here is mutate the length column, right? And so now this has the number of characters for each of those speeches. Okay, so it's kind of hard to understand unless we visualize it. So let's plot it. Boom, make this bigger. All of a sudden, we've got, a pattern. I mean, they seem to get longer and longer and longer and longer. And then someone finally passed the law that said the State of the Unions can't be that long. I'm just kidding. They didn't pass that law. But we all collectively agreed. I don't know. I actually don't know the story behind why those all got really short. Save these outliers. But here's another thing we can do. We can look with, instead of, right, so string length was used to calculate the length of the speech. String count can give me a count for every mention of healthcare, right? So you can try this with various keywords that you may be interested in. But now it's going to say, okay, group by speech, and then give me all this other stuff that's going to be helpful in plotting it. And then count the number of times healthcare's kind of used. And suddenly I have something like a kind of Google Trends output where I'm able to kind of get a sense of how often healthcare was used, right? You can imagine, try economy, try some other words. Here's economy, right? And so then you can start thinking, hey, wouldn't it be cool to let readers plug in their own or from a pre-populated list of keywords and pull down and compare different things? So I included a link over here, which is a Shiny that I built when I was still at Northeastern for a bunch of kind of network and social scientists that had polled Twitter data throughout the whole pandemic. And this compares a bunch of different words, by geography and by partisanship and these kind of interesting things they had for looking at like mask versus lockdown versus some other kind of words, that were tweeted by people. And then those Twitter profiles were connected to voting files. Okay, you're like, that's a whole can of worms that I'd love to get into. Okay, so let's do a lightning intro to sentiment analysis because we don't have too much time. But basically what we were doing for all that, n-gram analysis was looking at single words and two-word phrases, and then learning to kind of look for them, pluck them out, count them, visualize them. So what sentiment will do, so let's just pull these in. You don't even need Bing. I think I'm only going to use Vader. Vader should have run this on May 4th. Vader is like, there's arguments because you can get into this with the academics as to which lexicon's better than another one. They're all bad, right? Like Lennian models, right? They're all an approximation of understanding the kind of sentiment of a speech or a corpus, right? General rules is, the larger your corpus, the better these things are going to be, right? It's better to kind of infer the sentiment of something, right? Let's say over the course of a whole book versus one tweet, right? That kind of makes sense. So what Vader, this lexicon does, you can see right here, we can kind of inspect it, right? You are assigning words, and generally they do things like ask mechanical Turkers, and then take an average of what the Turkers have assigned each of these words. On a scale from, what is this, -2 to 2, I believe. Okay, dynamitic. How often are you going to find this in State of the Unions? Dynamiter is fairly negative. Dynamos is right down there in the neutral territory. Oh, sorry, it's -4. So you can see rapist is -4. Hell -3.6, and then on the other end you have magnificently, euphoria, sweetheart. All right, so now you're getting a sense of how these sentiment lexicons are constructed, and what words may not be appropriate or useful for an inspection of political speech versus what activists talking about the Chauvin verdict might be saying and using, right? Every context almost requires its own lexicon. So number one, I would say, go to the folks who are studying this, who are developing some of those, because they've thought and have some great solutions for understanding that. And in many cases, it's don't go with a off-the-shelf lexicon library, right? But let's do it anyway. So I'm going to store this sentence, Alexander and the terrible, horrible, no good, very bad day. And then I'm going to tibble it, and I'm going to put it in this tibble. All right. So once again, our value column has this sentence. And now what I'm going to do is the same that we did before, unnest each of those words, right? So you can see that I'm going to be doing that there. And then I'm going to join those words, and we have to make sure that, so those are all lowercase, right? One of the reasons unnest tokens converts them to lower is so that you can easily join in things like sentiment dictionaries. Parts of speech dictionaries exist as well, or you can make up your own lexicons. And so we'll join in Vader and check it out. And so all of a sudden we are left with terrible, horrible, no good, bad, and their associated scores. So you can tell Alexander and the Terra. So Alexander's not scored and the are not scored. And notice I didn't even use anti-join stop words. I haven't even used the stop words because it's almost a kind of, it's a step we don't really need, because you're not going to kind of, you may fold in some of those that have scores. That'd be kind of curious analysis, which stop words actually have sentiment scores across all lexicons. But then if I do an average of the 5 remaining that were scored, I get minus 1.28. So on a scale from -4 to 4, this is a pretty negative, with whatever I deem pretty as minus 1.28, right? Okay. So now, and that's called like bag of words scoring, right? There's a lot of debate and a lot of ways that one can do sentiment analysis. This is the most basic way. Okay, so now let's take the State of the Union object, because we have, as you'll remember, right? President, date, text of the speech, and let's unnest all of the words from those speeches. We don't actually need this anti-join stop word step. And then let's join in Vader, which is that sentiment lexicon. And doopy doopy doop, 152,000. So, and if you run, kind of each of these steps, I like to take notes on each of these steps and how many, like 1.87 million words were tokenized, 733,000 remain after stop words are removed, and only 153,000 were actually scored. So it's good to know kind of what coverage you're getting with something like this, or really any analysis that you're running on a corpus that large, and account for, at least mention some of those as caveats. And so then using, tidy and things like ggplot, we can do things like just answer questions we have, like, hey, of all the presidents, who was the most negative, right, in their State of the Union speeches? And so if I run this, right, group it by president, get an average score, right, for that president's speeches. So that's going to take all their State of the Unions over their, term or terms, right? And then give them an average. So imagine in your head, you could do the same thing here with tweet, right? Or you could do the same thing here with screen name if you're using social media data, right? And I could get the average sentiment of Trump, for instance. Okay, and so then I'll plot that. So I have each of those presidents, and then I have an average score. And I have an average score according to this sentiment lexicon, right? Vader. And so we have folks like FDR at the most negative, and folks like John Adams on the top. I'm not going to give you my analysis, mostly because I don't know, I haven't looked. Okay, other things we can do. Imagine again the Peter Aldis analysis of his State of the Unions, right? Why don't if I group this by the State of the Union speech and date, and then get a mean score. So instead of the length of the State of the Unions, I'm going to get an average score of that specific speech, right? And then compare it to the rest. And then if I plot that, it looks like it's getting more negative, but I don't know. It's a little flat. Like I wouldn't call it, if I saw that with a relationship between vaccination rate and vote margin, I'd be a little skeptical of making any claims. But you may want to look for a lexicon that covers a whole lot more of those words than Vader did, right? Vader was built for social media analysis, as far as I remember. So maybe not the most appropriate lexicon to use on State of the Union speeches. Okay, I think I have a few more minutes, right? Let's jump into, we could do Trump tweets. Why not? There's, you can do this. You do this on Congress people. You can do this on, we did this for the Chauvin verdict. We put together with the help of academics, a bunch of elites, say 150 elites that tend to be followed by Democrats and what they tweet about in terms of Chauvin and Floyd, and then 150 elites on Twitter that tend to be followed by Republicans. And then you could look and compare what the kind of tenor of their kind of commentary and their reactions to the verdict were. You could do the same for COVID-19, right? Kind of get a sense of how folks, you need to construct and then kind of split that, but the tools remain the same. So what I'll do first is I'll read in, this is just direct from the Trump Twitter archive, right? Pull them in. I'm going to mutate who hasn't dealt with fixing dates every single day of your life. And then we'll glimpse this. And so we have created at, and we have, okay, text of the tweet is right here. Okay, perfect. So I'm going to pull, so here's the Trump object. I'm going to do a couple things I like doing. Lubridate is awesome. I love doing things like, let me kind of group these by day or by hour or by month or by 3-day span. You can do tons of cool kind of groupings using Lubridate and Floridate. And so I can look at day, I can look at hour. So I'm going to mutate those in, and then I'm going to unnest the text of the tweet. I'm going to anti-join the stop words, which not entirely necessary, and then inner join my lexicon, right? And then you can see here, I'm just stringing these all together. I can group it by day, or hour if I want, summarize the average sentiment of each on each day, right? So what was the kind of average sentiment of the Trump tweets on that day? Run that all, and I've got a tibble, right? That looks like this when I visualize. Oh, that's a lot. I think the reporting challenge here is, can I explain any of these big jumps, or are they explained by the size of the data, right? That's one of the large issues that I've dealt with, that I think everyone deals with sentiment is, like I was saying earlier, the smaller the corpus, the wider your swings are going to be, right? The smaller your corpus, the more that one mention of kill or fire is going to tug at the average sentiment. You know what I'm saying? So that's something to kind of inspect, is how much of this effect is a kind of, it can be explained by the size of the words that I'm scoring. And that's, okay, so that's kind of one large caveat there. But, okay, so this, maybe I can make up a story about election season or campaigns, or, the day of the election. But what I did, just kind of looking at this quickly, was, okay, wait, why don't I use string detect, filter his tweets for every tweet that mentions Republican or Republicans, right? This will take Republicans as well. Although unfortunately it won't take Republicans if it's capitalized. So let's throw those in. If someone has a better kind of regex, let me know. But string detect, and then what I'll do is I will group it by day, right? So I'll unnest the tokens. I'll fold in the sentiment lexicon, and then I'll look at the kind of score per day of Trump tweets mentioning Republican. And then I'll do the same thing for Trump tweets mentioning Democrat, right? So I'll run those two. Then I'll bind them together. And the reason you can already guess why I mutate in the name Republican as the mention column, is so that I can quickly visualize this and then facet it or color it by mention, right? So once I've kind of bound those things together, there's probably another way to do this. This is the way that I've done it. Is then plot it like this. And so all of a sudden I'm seeing that Trump on average and consistently, because I think these early years, it's just not as much data, right? That's, I think, partially explaining, you can tell by the intervals here, but is consistently mentioning Democrats in a more negative light, at least according to the Vader lexicon, and summarizing it by day. You can go play with this and summarize by week, by month, by hour, and I encourage you to do those to kind of get a sense of how much this changes. And so I'm not going to run this, but you guys can see this. And that is, we ran this on January 6th for Parler data, looking at what was happening on Parler during Trump's speech. And you could imagine, right, we had, thank God, several days to kind of work on this. We looked at a lot of things, right? We looked at, several days before and through and after his speech. We looked at hours before and after his speech. And in the end, we used just day of, and did something which, and I'll credit Mitchell Thorson on graphics at USA Today, which was awesome. It was just kind of a dream of mine for years, which was like, could we annotate and explain to readers what was driving that sentiment at that point by giving them kind of the top phrases, right? So here's the top bigrams at that point in time, and then how much each of those were scoring, right, in our kind of average measure, and kind of show folks over time kind of what that was. And then the trend line here is kind of your average Parler day. And so if you were to plot, and we did at one point, average Twitter, it's like way up high right here. So Parler is definitely more negative than Twitter, which you don't need me to tell you that. Okay, and so the codes here to kind of run that. The two things I want to show you here before I think we wrap for questions is, okay, you're noticing here I'm doing that kind of bigrams from the Tidy Text book, like that you can kind of understand. This thing up here is a way to filter, because God help me, I need I need help with filtering dates. But this has been a way I've found, thanks to Stack Overflow, for converting dates to a kind of numeric, right, value, filtering between those values to get very specifically posts between those times, and then just remove that column, right? So then lastly, I'll just show you this. What I'll do is I'll summarize the kind of numbers, and I'll just run this so you can see it, see how long it takes. But what I'll do is I'll summarize, okay, how often does that bigram show up, right? And then I don't want just a raw number, because raw numbers are horrible to compare. If after Trump's speech, there were 2 times as many Parler posts, right? I need a proportion. And so then what we're doing here is kind of get a total of the posts mentioned in that hour, right? From 11:15 to 12:15, and then divide the number, all right, of those bigrams by the total. So I get a proportion. I'll do the same thing for hour 2, right? And then what I'll do is I'll merge them together. And then this is probably not the cleanest way to do it. I'll summarize a change in proportions from the second hour to the first hour, or vice versa, right? So that gives me a sense of what kind of jump I'm seeing in terms of how often that phrase is uttered, right? So the jump from hour 1 to hour 2. And I've done this I'll do this for day 1, day 2. I'll do this for hour 1 to 2, hour 2 to 3, hour 1 to 3, hour 2 to 4, right? To kind of get a sense of the movement in the speech and in the corpus. And in the end, what this gives me is something that looks like this, right? Which is Civil War, voting machines, president-elect, Mitch McConnell, Mike Pence, Pence traitor, a lot of that kind of stuff. And then I get a sense of how many times it was mentioned, divided by the kind of total phrases. I think what I did, sum of n, total n-grams mentioned, right? And I brought all of this by the academics because I don't trust myself. And I want to get a sense of exactly the way that they would approach this problem. So you want to make sure that you're, like with everything, using the right denominators, accounting for things like stop words, accounting for, am I counting all the words or am I counting the bigrams? What's the kind of most appropriate relationship to depict here? And when you arrange it by kind of the largest jumps between hour 1 and hour 2, Civil War just jumped to the top. And so that really became the kind of thrust of the story, and then kind of contextualizing around those phrases. So all of that happened before, pen hit paper, right? It was really just exploring the data set, thankfully, for a couple days before we kind of zoomed in on what it was going to be about in terms of the kind of larger relationship between what was happening on social media, not just Parler, and January 6th and his speech. So I think I'll stop there. I've been ignoring the chat. There's probably like 10 ways that people have done things better than I. So I can't even pull it up. How do I pull it up? Here it is. All right. String detect to lower text. Yeah, to lower is an awesome little function. Okay, well, do we have any questions or maybe not? Maybe we just go to mapping.
Thanks so much for walking us through this. This is really great. I mean, it's like during those debates where you see like the on CNN, the people like reacting in real time on those dials. And then you could like plug this to a Twitter feed and just see it in real time.
And the number one caveat, sorry, last thing I'll say is sentiment dictionaries suck. Like sentiment analysis, like your answer to your editor should be wait. like no, we're just not going to get anything that's noteworthy or interesting, by just kind of doing a broad brush analysis, like who was more negative, right? I think that the second kind of step there is who's developing more interesting ways to kind of understand speech. And so the computational linguists are like my rabbis for these kinds of stories. Like run it by the folks that deal with this night and day, and then run it by the political scientists that actually don't touch computers or code, and see if it lines up with the years of research in terms of things like campaign speech and et cetera, et cetera. So there's a lot to learn, and I'm scratching the surface. But yeah, thanks everyone.
Very great. And like all this technology really just kind of came out in the last year, right? These packages and things.
Yeah, Tidytext is probably 2 or 3 years old. But yeah, people are doing, there's some really great stuff. And actually we cross-validated or validated that roll call analysis with a model that was trained on IMDb reviews, and both of them spit out the same answer. So I think if you're going to try to get into sentiment and say something defensible, you got to try it against every lexicon, and then go bring it by the folks that are developing models, right? Now, BERT and Elmo and GPT, like all of that stuff is spitting out sentiment models. So that's another way to kind of check your work.
Very cool. Well, thanks so much for taking the time and walking this through for everyone. Next up, we've got Aaron Kessler. Is he out there? You out there, Aaron?
I'm here. Hello.
Great. Well, I'll let you introduce yourself and talk about what you're talking about.
Hey, everybody. It's great to be with you. This is a great session. Thank you, Andrew, for doing this whole afternoon. Yeah, I'm Aaron Kessler. I'm currently at the Bloomberg Industry Group. I'm doing data stuff for a number of years, all kinds of other reporting beats along the way as well. So actually, some of what we'll talk about today, I'll just bring in some political data because I figure it's DC and so forth. But I'm going to be talking about getting started with GIS and R, which I guess there's a lot of interest in that. So we're doing 2 sessions. So I'll hopefully at least get your appetite whetted here, and then Hannah's going to come in after the break and talk about even more exciting stuff. So if you've never done any GIS at all in R and are curious, hopefully you'll get a sense of that. If you've done a little bit and want to learn a few new tricks, hopefully by the end of our day today, you'll know that. So let me see. Can I share my screen from here, Andrew? Let me try it. Let's give it a whirl. Okay. There we go. Actually, this is, I've got a little GitHub repo for those of you that want to look at this afterwards. It should be linked in the sheet, but I will share it here as well in the chat, assuming I could find the chat window now, which is hiding in there somewhere.
Oh, I
There we
took
go.
care of it.
Oh, perfect. Thank you. Awesome. Okay. So again, here we are in R, our usual spot. I think someone made the comment earlier. It's interesting to see what kind of appearance we all like. So I guess this is sort of my favorite here in terms of a darker background. But I hope this at least works for the code standing out. If people have trouble seeing, please just let me know. So what we're going to kind of mention is a few different pretty standard R packages for doing geospatial work. But a couple questions that you might have in the beginning: how do we even get stuff into R in the first place? So there's two primary ways to do that. One is you get a file like you've already been doing. If you use QGIS or ArcGIS, you get a shape file, a GeoJSON file, whatever it is. You can bring those into R. We're only going to look at shape files here, but you can pretty much import almost anything that you could find. Even PostGIS databases, TopoJSON, whatever. Most of the time you can get it in here. The other way to get it is actually by using R packages that are designed to bring that stuff directly into your session. So the one we'll talk about here is called Tigris, which connects to the census data and is able to bring in census boundaries kind of on the fly. So there's all kinds of different ways to bring the data in. And then in terms of what you do with it once you get there, there's sort of a plethora of options, and they've been growing, day by day. So we're going to talk about just a couple ways, primarily using something called the TMAP package. But there's all kinds of other things you can do as well. So let's go ahead and take a look. So again, this is just sort of a little intro here, designed as if I could, so you could read it afterwards and have some kind of understanding of what's going on. But I'm not going to aim to read everything here, because you'll have eyes. You can certainly do that too. So the first thing we're going to try to do is just a quick map if you want to plot points, right? So you think, okay, I have a map, I want to create a map in R, I want to stick some locations on there. How do I do that? All right, so there's, again, a few ways. We'll look at the TMAP way. So to start with, I'm just going to make sure I load these libraries at the top, because I almost forgot to do that. And then Tigris, again, has a whole bunch of different boundary files that you can just bring down essentially almost effortlessly. So we're going to bring down some states here, but it has everything all the way down to census block groups, school districts, congressional boundaries, as we'll see in a second, some other kinds of things, counties, of course. There's a few little ways you have to do it if you want to get very small geographies from the entire country. We're not going to talk about that right now, but I'm happy to answer questions about that. But for now, what you'll see here is we just use this command, Tigris, use this function states to then bring down a file of states. And we're going to say that we're going to have the resolution be 20 M, which is pretty good for the whole country. If you're dealing with one state or a specific region, you might want to get more detailed. That's fine. And this cartographer band go ahead and run there. Pretty quick. Again, it's downloaded the file. We now have an object here. And if we take a look at it, what do we have? We have what looks, for the most part, like a data frame. So I'm going to emphasize this pretty much the entire half hour here. But in terms of the way R used to deal with geospatial data, it was kind of clunky. It was difficult to use, and you had to go through a lot of different steps to make it sort of wrangle it for you. Now there's this new type of objects called simple features, SF. There's a package called SF, and there's lots of other packages that work with simple features. And that makes it, as the name sounds, a lot easier. So a simple feature, as you see here, looks very much like a data frame.
Aaron, could you zoom in a little bit?
Zoom in?
Could you zoom in the text a bit?
Absolutely, yeah. Thank you. Get bigger here. So simple features by their nature, let's do this while we're talking here, act very much like data frames. You can see the columns here, and yet there's a column on the end all the time that has the geometry. And the geometry column is quite large. It gets this name multi-polygon. and it's got all of the geospatial information included there. What makes this nice, and you'll see this here in a little bit, is you can actually manipulate these files. You can do filters and joins and other kinds of things, very similar to the way you're already familiar with doing the same with a data table or a data frame. So this is just a much easier way to deal with geospatial data. And so I'm gonna, if you haven't played with this stuff before, I'd say just skip the whole SP package unless you really have to, and go straight to SF, simple features. But anyways, this is kind of what the data will look like underneath the hood. And you get a little bit of information here. So you can see it's a simple feature collection, tells you how many fields you've got, how many features. This multi-polygon, it gives you the bounding box, which we're not really going to talk about here, but that's basically the extent of your map. And then this is going to be pretty important here, which is the CRS, the coordinate reference system. We're going to touch on this in just a minute, but that's particularly important when you're trying to layer things on top of each other. How does the map basically shaped on the Earth? But that's it. So this kind of looks like what appears to be a list of states, right? And then it has this multi-polygon geometry associated with it. So because it does, you can actually map that out. And so there's different ways to do it, but the one that I'm going to show you here, which I kind of think is pretty straightforward, is using the tmap package. And so tmap has a few functions. They all start with tm underscore something. And the main one is tm shape. So you have to feed it some sort of shape so it knows what to do with. And then here I'm going to say, okay, then plot polygons. Now, the thing to keep in mind is that if you use ggplot2 as well, and you're a little frustrated sometimes that they still use a plus instead of a pipe, tmap is like that. I don't know if it's ever going to change. Maybe it'll change the same time that ggplot changes. But for now, just to be aware, so you don't get too confused, that there is indeed, instead of a pipe, just use the plus sign, and it operates basically the same way. So right now, we've downloaded this. Again, we've downloaded this file from the internet, thanks to Tigris. I want to actually see a map. So I'll use this tm shape. I'll feed it the name of our object here. I'll feed it to polygons. And with this little bit of code, it's going to know enough. As you can see here, now we start to get something visual. Now we get a map. Now, of course, because the US has some territories in different places, and it has Alaska and Hawaii, this is by default going to give us the full extent of everything. So for the purposes today, we're just pretty much going to look at maps of the lower 48. And at the very end, if there's time, I'll show you a little bit about how to deal with some of that for Alaska, Hawaii, Puerto Rico, and so forth. If we run out of time, at least it's in there at the end. Okay, so but let's say I want to focus just on the lower 48. Well, how do I do that? You can manipulate these SF objects very much like you can do it just with simple dplyr commands and other ways that you might be comfortable filtering other data sets. So let's go ahead and do that. Let's just filter it down to just in this case, the continental US, the lower 48. So one way to do that, of course, is to use the codes based on the states. And the Tigris package itself actually comes with a built-in FIPS code database. And I found myself using this for all kinds of other purposes that have nothing to do with mapping. It's kind of a helpful little thing. But if you click here, you'll see, here it is. Basically, for every county, it's got the relevant FIPS code for it so that you can use that without having to go out and download, find something, load it in. So what I'll do here is I'll go ahead and create a vector of the 50 states in DC, and then filter that down. And we'll see what we get. This is just going to count how many rows we have. You can see it's now 51. And then we'll just go ahead, and this is something I included here mainly because you'll find yourself doing this quite a lot. You get any geographic data involving the United States, a lot of times those outlying territories are there. You just want to get down to the 50 states. So you can use basically create a vector very much like this to accomplish that. In our case, we're just going to filter yet again. So this is just a regular tidyverse dplyr command. We're going to filter for where in this case, the state abbreviation field is not equal to Alaska and Hawaii. I'll just run that. And now you can see we're down to 49. This includes DC. So if I plot this out now, again, we're running the same command as before, same function, but now we filtered our states geo to be, in theory, if we did it right, just the 48. And there we go. So now we get something that looks a lot more familiar, I guess, if you're going to do mapping of the United States. And again, at the end, if there is time, I know we're kind of, we've got a half hour here. I'll tell you a little bit about how you can do things with inserting Alaska and Hawaii and so forth. But for all intents and purposes, hopefully you'll get the sense just looking at the continental US. Okay, so we've now created, with just a few lines of code, we've brought down a map. We've displayed the map. What might we want to actually do with that? So tmap by its nature has a whole bunch of different commands. We're not going to go through all of the different functions now, but just to show you kind of how simple it can get to get started, is you can feed in a parameter, you can feed in an argument that you want to symbolize by. You want to create a choropleth map, and we'll do that here. So I'm just going to use it right here. You can see this looks identical. We're just adding in under TM polygons a land, which is the land area field. And just by doing that, I'm also giving it an ID. We'll talk about that later. It's not really necessary, but it helps a little bit in certain ways. Just by adding that a land, it'll just by default automatically create a choropleth map, and then you could start tweaking that as you might see fit based on the number of bins you want, the colors you want, all kinds of other stuff. But just by feeding in that value of the column that you're interested in, it's automatically going to go ahead and create that for you. So that could be, again, very helpful to build on. If you want to add things like labels, again, we're not going to go through all of that now. Just so you're aware, you can do all kinds of customization. So as an example here, we're just going to add a TM text, which is one of the functions that let you create those kinds of labels. And we'll say, hey, you know what, label the states based on their ST-USPS, which is the abbreviation, and give it a little size of the text. So if I run this one here, you can see now all the states have their labels. Now, the nice thing about working in something like this is if you're in a newsroom where you have all kinds of different graphics folks you might be interfacing with, and it's not uncommon for a lot of them sometimes that they'll use Illustrator and you want to give them something. You can actually export these, and we'll talk about in a second. You can export these to vector files like PDFs, SVGs, and whatnot. They can bring them in and touch them up and style them wherever they want. So it's a pretty common use case where they're not going to have to do all the math involved in figuring out how these things need to be shaded, especially if you're dealing with things even greater than or smaller than a state level. But you can do that work. You can hand it off, and it's pretty easy for them to bring that in and then change colors and text fonts and whatever as they see fit. But you can do quite a lot even just using R itself to get to the point where something is certainly publishable. It's more for newsrooms where they have a very specific style, and they might not let you necessarily just use the map you've made. You can get them 95% of the way there. They can touch it up in Illustrator, and then off it goes. So let's just talk about two quick concepts. The cartographic boundaries, this CB you saw above, what does that mean? It basically means that that's going to follow what you would expect to see when you look at something like Michigan up here. So in other words, it's going to factor in, for the most part, bodies of water, what those lines really look like, versus if you don't do that, and I won't do it now because we just don't have a ton of time, but if you go ahead and play with this, take out the CB equals true, you'll see that this boundary between the Upper Peninsula and Michigan will be gone. If you're in Virginia, the North Fork and all that won't have its usual shape. So for the most part, you almost always want to make sure you use the CB equals true. But that's what that means. There's some instances where it might not matter and it might not be of interest. But you always want to kind of be careful that you're not inadvertently leaving out these coastlines, because you'll definitely hear from folks about that. The other thing to keep in mind is this thing called the coordinate reference system. And we're not going to do a whole ton on that right now. I would direct you to this very helpfully named website, IHateCoordinateSystems.com, which is quite, despite its name, informative. But the idea behind a coordinate reference system was when you think about the Earth, right? The Earth is round. And so any map that you're going to make has to represent that round surface in some sort of two-dimensional representation. So a coordinate reference system is an attempt to make that as accurate as possible for certain purposes. So the one that this is actually in, NAD83, is a very common one for the US. Any GPS data that you get, there's one called WGS84. You don't have to remember any of that. You just need to be aware that these things exist. And especially if you're looking at something, say, at a state level or at a local level, you want to be aware of what the right coordinate reference system is. One, so it looks proper, right? You don't want things to be distorted. But also, if you're going to do anything involving either layering one type of data on top of another or doing any kind of joining, you want to make sure that those distances and those locations are being properly drawn, and that they're being drawn the same for every layer. So that's kind of what we'll just sort of emphasize here, but just be aware there's a ton of these different CRSs. It's usually not that difficult to find out which is the right one for your use case, but you just want to make sure you keep that in mind. So if you want to figure out, hey, what is the CRS for a particular geospatial data set, SF has a nice ST_CRS. I will admit it's a little confusing because the SF package, all of their functions start with ST underscore. You know, so just something to keep in mind. It's easy to start typing SF underscore and go, well, how's this working? It's always ST. So in this case, ST SRS, if I run this, you'll see that below, make this a little roomier, this is giving us the reference system. So here it's NAD 83. That's a pretty common one for US maps. That's what the census is using here. And then there's this, what they call well-known text, which is kind of a text version of that reference system. We'll talk just a bit about why that's important in a second. But now that you know what that is, you've got enough information to make a decision about how you want to treat it. Certain maps, for example, and we'll mention at the end, you know, this is obviously a little bit more stretched out. Some newsrooms might always prefer what they call the Albers projection. So you might want to reproject this into an Albers projection and so forth. But for now, we're going to talk just about the importance of having whatever layers you're using be on the same CRS. Otherwise, you could get yourself into a little trouble. That's how you figure it out. Okay, so let's actually plot some maps. We've been talking here a little while. Let's actually do something. I don't want to run it through the whole time and actually show you some maps. So what we'll do is I'm going to bring in just a sample of cities. There's going to be about a couple dozen cities here. I'm going to bring in a regular data set from a CSV file. We can see it here. Here's a list of cities. And here are their coordinates, their longitude and latitude coordinates. So if you have that information, you can translate that into a geospatial point object and stick it on your map. So let's go ahead and look how to do that. To do that, we'll use the very helpful, so I realize the chat window is actually not visible. I have my thing up here. So let me make sure I can actually see it. So if you'll have questions along the way. Okay, good. I'm just going to put this up on over here just so I can have it facing here. Okay. Actually, that's an excellent question about dealing with very large files. I don't actually have that in this thing, but I'm happy to talk about it. There's a good way to, there's a package called R Map Shaper, which lets you what they call simplify a geospatial object. So a common way to do that, in fact, I may be able to even pull up an example by the time we're done here this afternoon, is you get a fairly large shapefile or even something where you download something from Tigris, it's just too big. And so you go ahead and simplify it, especially for something like the United States, and it vastly can improve your speed if you're struggling along. Again, it's just a way of processing that geospatial file. So I don't have a quick example of that now, but if there's time, even at the end of the day, I'm happy to show you how that works. Short answer is yes, that can be done. So you'll reduce this until 10% almost of its size. And if you're looking about the United States, that's perfectly fine. And then the things just fly by. For these, they're going pretty quick anyway, so I didn't bother to show you that, but that's an excellent question. Okay. In terms of how to coordinate, or sorry, how to translate a data set that has coordinates, lat longs, into a spatial object, you have the very helpful st as sf. This is the packet, the formula or the function in the package that translates a longitude and latitude into a spatial object. So I'm going to go do that. I'm going to feed it this CRS. And sure enough, now I have cities. Oh, helps if I actually don't highlight the wrong part. Hold on one second. Let me do that one more time. There we go. So now I have cities geo. And if I were to take a look at this, you can see it now has the information we had before, and it's created that geometry field for us. So the lat and longs are now gone, and the actual spatial information it needs to know where to plug those things on the planet is now attached to our cities. So like before, I'm just going to go ahead and run that STRS, or sorry, the STCRS to see what we have. And you can see, in this case, this is indeed NAD 83, right? And then this one underneath, also NAD 83. So that's cool. So you're like, that's good, right? And so in theory, that is good. The thing to be aware of is that it's probably good just to make sure they're identical. So in other words, what I mean is that the well-known text here, as you can see, is slightly different than the one underneath, right? It's a little bit longer, a little more verbose. And that's probably okay, but it's always good when you're plotting points on a map, especially if you want to do anything with them, just make sure they're the same anyway, exactly the same. And so the way you can do that is to assign one to the other. And so that's actually what's happening right here. So I'm going to say, okay, for cities geo, I want to use st transform, which is assign a coordinate system. And I'm going to assign it to the same CRS that states geo is. So when I run this line, and again, it's pretty quick to do that. Now, when I go ahead and run each of these, you'll see they're indeed identical. This can be a little confusing sometimes because you're like, well, they're in the same CRS, right? They're both this NAD83. Why do I need to go through this step? And the shorter answer is it might be like 80% of the time it won't matter, but the 20% of the time it will matter. It's always better just to do it. And you can see how easy it is to accomplish. So now that I've done that, let's go ahead and get some points on this map. So to do that, you build this. And for those of you that are familiar with ggplot and so forth, those kind of workflows, very similar here. I'm just going to take, this is just what I had before. So this is just the map of the states. And then I'm going to hit another plus, which again functions just like the pipe here. And then I'm going to feed yet another layer, this time the cities, which are going to be plotted as dots. When I run that all together, I get my dots. Now these dots are not very easy to see, right? So you have the ability to fiddle with it. So in this case, I can change the color to red. I can mess with the size. Okay, now maybe that's a little too big, but you can sort of see how this is playing out, right? And then once you get a map, essentially the way that you like it, you can save that as an R object in your environment. So that's what I'll do here. I'll just call this my map. And then you can see it's up here. It shows up essentially as a list, but it's basically the map object. And that map object, if I just call it, so now if I just call my map, there it is. These are slightly smaller circles. So once I have a map, and let's say this was, the end of my process, great. Let me get it out of here. Let me do something with it. There's a few different options to save it. If you are in RStudio, you can just come up to the Export tab. You can save as an image. You can save as a PDF. Again, if you're sharing with someone who's going to be bringing this into some sort of graphics program like Illustrator, you always want to use PDF or at least SVG because the static image isn't going to help it very much. You want those layers to be preserved. Or you can do it programmatically using the very helpfully named tmap save. And there's different sizing parameters and resolutions and so forth you can feed into this. By default, if I just run this, so I'm just going to feed it my map. I'm going to call it my map PDF. I'll just stick it in the root directory. When I run this, you'll say get a little output below. It's been saved. If I go over to my files, here it is. And there's the map. So in terms of how you get it out, it's pretty easy to go ahead and export these things when you're done with them. Another thing you can do, and this is depending on your use case, you may find helpful or not, is you can actually save map objects as an RDS file, just like you would a data frame or anything else. So if I were to go ahead and do this, you'd see now there's a little file in here, now map RDS, and I can then bring that file back in at any point to any other project and use it. And so one of the reasons that you might actually want to do this is, let's say you have a very complicated map, it takes a long time to process, as some of you mentioned, your map. Once you get to that end result, you don't want to have to replicate that entire flow. Let's say if you're knitting up a markdown document or something like that. So you can just save that result, and all you do at the end is you load that result into your new markdown document or website function. So to show you that can work, here it is. I'm going to read the RDS in as a totally new object, map to include. And now when I run map to include, here it is. So it's just something to keep in mind. If you find yourself you're spending a lot of time processing a map and you're like, well, now I want to show it to somebody, I want to share it, you can sort of share that resulting file. And the nice thing is it takes all of that tmap information and actually keeps it in, which to show you that really works, one of the things about tmap, which is kind of fun, and we're not really going to get into all the particulars of Leaflet today, because there's a whole Leaflet package which lets you do all kinds of stuff as well. But if you just wanted to create a map that was a Leaflet map that looked very much like this, tmap actually lets you do that with just one line of code. It's this tmap mode. So there's two modes, you'll see them here. One is view and one is plot. And if you switch the mode to view, which I'll do right now, and you can see it says tmap mode set to interactive viewing. If I now take the my map, right, I take the thing I've saved and I regenerate it, it's going to do that as a Leaflet map. Now, again, this is not too fancy, but it is something that can be done with pretty good degrees of specificity using tmap. And if it's not quite enough, of course, you have your Leaflet package too. But this is an actual Leaflet map, and you can see if I click on, the city, I get little pop-ups here, so you can customize those, you can play with that. So if you're looking to create interactive content to some extent, you're able to do that using both using TMAP and winding up with the same map. So for example, I have one interactive version, I have one version that might be very similar, almost identical, that I'm exporting to PDF to share with the graphics team or whatnot. And so you're able to switch back and forth. And so you see, I don't even have to do anything to the object, but just switch it back to TMAP plot right here. Again, I'm calling the same object. It's now switched back to plot mode. So when you start up R and you start TMAP, by default, it's always in plot mode. But all you have to do is switch it to view mode if you want these to become leaflet maps by default from that point forward. Okay, so that's kind of cool, right? All right, so let's actually look at another example. So we've talked about plotting maps. Let's talk about the choropleth maps. They can symbolize maps, the other big thing that we tend to do most of the time. So let's look at some, since we're in DC, or most of us, we'll look at some demographics from House races in the last election cycle in 2018. So let's go ahead and bring that data in. So here I've just got a data set of districts. Let me take a look at what we have here. You can see we have each district in the country. We have sort of a rating, right? Like the political report and so forth would be ratings of how competitive it is. And then over here, we've added in some demographic and economic indicators. So is this district above or below the median average, or the median for the percentage of non-white population or percentage of college graduates, right? And so you've got different measures here, and then you have who won these districts over the last few elections, presidential, then the House. Okay, so that's a pretty standard data set you get. And you want to be able to go ahead and marry that up to a map. So how would we do that? So since above we showed you Tigris, I'm going to show you how to just get something in out of a regular old shapefile. So in this case, attached to this repo, we have traditional shapefile here. This is from the census. This is their boundaries for congressional districts. Right, it's got the usual stuff. So this is something that you probably have at your disposal already if you've been doing GIS work. But anyway, so you get that data set, and you can use this stRead. Again, it's st underscore, but it is the SF package to read that shapefile. And you just give it the path both to the folder and then to the actual .shp file within that folder, because of course shapefiles have many files. You point to this one, it does the rest from there. So let's see if this actually works. So if I run this, I wind up with a file or an object named stgeo. We can kind of see what that looks like. You can see it here. It's been brought in. It is a simple feature. It's got 437 features, 8 fields, and so forth. Here's the CRS, as we talked about, and then a little bit about what it looks like. And here enough, you can sort of see how it looks. I've got the window condensed. If I didn't have that, it would sort of spread out like a regular data frame. So now let's go ahead and join them together. So the nice thing, again, about these simple features is you can use a lot of the same packages that operate in the Tidyverse framework and even others. You can use those joining functions to join spatial data to non-spatial data in this case. So in this case, I want to take, I have my map. I want to go ahead and join my districts so that I get all of this information associated with the map. And I can do that using just a regular old inner join. And here I'm joining on the FIPS code, which in one case is GeoID capitalized, in the other case is not. So I listed twice. I'm going to save this as a district map object. Now when I have that, let's see if it works. Make this a little bigger. And you can see, of course, here is all of that stuff. So now I have both. This is the geography or the geospatial information here. And then starting right here is my table that I had brought in. And it's all joined up where it needs to go. And at the bottom is the geometry. So now that I have that, I can actually start symbolizing based on that. First thing I'll do is I'll just take away Alaska and Hawaii, just to make it a little easier for everyone to see at home. We'll make sure we have a plot. And then we'll say, okay, can I plot out that map? Well, here it is. So it worked, but I still don't know, did it really join, right? I saw the data behind there, but right now this is just the map. Well, let's add something in. Let's say I want to see the who won, did Donald Trump or Hillary Clinton win that district in 2016. So again, I'll just feed in that variable here, President winner 2016, which is Republican or Democrat in this case. And when I run this, it's going to go ahead and symbolize that for me. So now I've taken data from the outside world, so to speak, on election results. I've married that up with the geospatial data, and now I can actually start analyzing it in different kinds of ways. So let's say I want to say, well, what does it look like for percent graduation from college? I just feed in another variable, and now we can start to see that going on. And again, this is sort of the default colors. You can customize the colors to your heart's content. You can customize all kinds of stuff. Just want to make sure we can flow through this pretty quick. So, all right. The other thing you could do is you can now filter that geodata set for certain things that you're interested in. So let's say I only want to see the Republican districts that were basically leaning towards the Democrats that year. I can do that. I can say, okay, I'm going to take my district map object. Again, this is the map object we've just been mapping with, right? But it can operate very much like a regular data set. So here I'm applying just a regular filter, and I'm saying, okay, show me where the incumbent in 18 was a Republican, and where the race rating was either likely lean Democrat or toss-up. So basically, it was one of the most competitive districts, right, that Republicans held. So I can actually just run that filter, save it as a new object here. I'll call this, Republican held Dem advantage. You can call it whatever you want. And now I can map that instead. And there it is. Now, of course, you can kind of see the problem here, which is it's mapped those districts, which is real nice, but I don't see the rest of the country. So, I mean, I can use my imagination, but maybe there's a better way. And so there's several ways around it, but the easiest way is you just layer them on top of each other like you would in any other mapping situation. So here, what I'll do is I'll layer in the regular district map. And then on top of that, I'll layer in my new, highlighted districts, so to speak. I'll give a nice red color so I can see them. And when I do this, now I get everything together. So there we go. And you can use this kind of method to do all kinds of stuff. You can even go ahead in theory, and instead of just showing all of these Republican districts as the same color, you can even symbolize them. So let's say I want to see those Republican districts, but I want to see it based on their college graduation levels, right, above or below. I can do that. And then once you have what you want, you can go ahead essentially and save that as yet another object name. So here I'll give it a little title. And again, I'm not going to go through all these, but you can kind of see how they work here. TMAP has some very good documentation about this as well. You can, there's all kinds of different ways that you can customize what this map looks like. And then just like before, I can go ahead and save it. And now over here, I'll have my object. And there it is, right? Again, it doesn't look beautiful, but it's working. And it did happen in 2 minutes. And so you can customize it, make it even nicer from there. All right, I know we don't have a ton of time, but let me go to just 2 more things here before we get to the end of time, which is it 3:45? I'm supposed to stop this, or 3:50?
2 minutes ago.
2 minutes? All right, I'm gonna do this real quick. We're not gonna have to talk about, for those of you that live in Alaska, Australia, or in Hawaii, I apologize. Okay, spatial joining, another thing you wanna have to be doing on a regular basis if you're doing any kind of journalism project, right? You wanna take things, see if they are in the same place. So let's look at our cities that we had before and say, okay, I've got these cities. Can I see what congressional district those cities are in? And you just think about this as applying to anything. I want to see whatever these things are, what congressional district are they in? Can I do that? Well, I have the cities. I clearly have the boundaries of the congressional districts, who just use them. So what I'm going to do is I'm going to go ahead and join them together. So first, I'll just sort of skip past it because we're short on time. I'm going to make sure they're part of the same CRS. So I'm going to do that here. And once they are, one of the things that's helpful to do is, first of all, just map them out, make sure they look like they're in the right place. If I saw a red dot like way over here, I know something was wrong. And then I'm going to use this st join. And this has different parameters you can feed into it, but the main one is where do they intersect? So this is going to show me where are, which district are each of these things in. I run the st join. And sure enough, here is the result. Now, if I want to simplify it a little bit and just see if it worked, I can select just those cities. And here you can see I've got the cities, and now I've joined it with the house district, which came from the geospatial file. So it was joined it based on the location on the planet. Now it also has the geometry, and the geometry comes with it no matter what. But if you want to get that out of there, let's say you want to share this with someone else outside of this, there's a helpful little function here, st set geometry to null. If I run that, you'll see, boom, it's gone. So this might be, I export this to a spreadsheet, I share it with everyone. So yeah, here's all the districts they came for. The last thing before I go, very quickly, the benefit of doing things in R, you might be using GIS in ArcGIS, QGIS, like, why do I need this? I can do the same thing. And the short answer is you can do that. Where this can really shine is when you have to do the same thing over and over. And this is, someone mentioned this a little bit earlier, I think, during the purrr session, and we're actually going to use purrr here. So let's say I go ahead and I've got my congressional district, and I want to go ahead and say, okay, I want to look at the breakdown of what the percentage are of people that went to college in every district in the country. So that's cool. And I could do that, and there it's done. I send it off, right? But there's a lot of different use cases where maybe you need to have each state individually on its own. So how might I do that? Well, if I wanted to do that, I'm going to go ahead and just join up this so we get the state name. I can filter like I did before and say, okay, I just want to have one state. I'm going to want California. Let me plot that out. There's California, right? Great. And it's actually done the binning properly. And I said, perfect. Okay, that's cool. Now someone tells me you have to do that 50 times. If you don't want to do that 50 times, you can feed this into a traditional R function. So that's what's happening here. Is this is a function that's saying, okay, take an argument, in this case, a state name, filter based on that state name of our district map, create the education breakdown, and then save it as a file. So now if I run this function, you'll see I have it available to me here. Now what I have to do is run it and say, right, make my state map for California. I see I get a result here. I can go into my files, and there it is. So once I show that I can do it once, then all I have to do is, again, using purrr, which was mentioned before, I can go ahead and create a vector of all the states in my district or in my map, which are here. You can see them across the bottom. And now I'm just going to use the walk function, which is very much like map, but it's for when there's a result. It's going to pop out like a file. I'm going to run this, and you'll see this will be a good way to end things. Here, I'll pull up the map here. Here's the empty folder. What this is going to do, it's going to say, okay, take the list of all of the states, which is here, feed them through this function of make map, and make a map of everyone. So once I have that in place, you'll see what happens. I hit this, all goes well. You can see it start filling up, and it'll keep going until every state is done. So if you find yourself in that kind of situation where you're repetitively doing something over and over and over again, R can be very helpful in that respect when it comes to geospatial work. It's probably a good place to end. Stuff that I didn't get to at the end, which you're welcome to look at, is how you could do route tracing, basically drawing like paths from one place to another. We used that pretty effectively in a recent project we did. And at the very end, you'll see in this, if you look at the repo, there's a little bit about how to deal with Alaska and Hawaii. But I think we're already a minute over, so I will stop here. Are there any questions before we break?
If anyone has questions, go ahead, please thread it in the News Nerdery R channel. And in the meantime, we'll just take like 2-minute break, and we'll come back for the last hour and 10 minutes of this entire thing, where we're going to go over more GIS, some Docker and R, and then GitHub Actions with R to wrap it all up in just an hour and 10 minutes. So we'll see you in 2 minutes. Okay.
Awesome. Thanks, everybody.
Hannah, are you there?
Yes, hello.
Well, I'll let you introduce yourself and talk about what you're going to talk about.
Hello, everyone. My name is Hannah Recht. I'm a data reporter at Kaiser Health News. I'm going to be doing a second part GIS. So thank you, Aaron. That leads really nicely into this tutorial. I just dropped the link into Slack. Let me see if I can share my screen. Sorry, I'm going to screen share, but just in case it's hard to read and for future use, I've shared the link to this as well. Can you all see the Firefox? And should be kind of zoomed in. So I'm not gonna like read this word for word, but I'm gonna talk about the code in here. So there's a lot of written words, but I'm gonna say some stuff that's not written down in here. So I'm gonna talk about sort of the second part of GIS is how to analyze things. So less on the mapping side, more on the spatial analysis side. And I'm going to talk about, drive time analyses in R. So what a drive time analysis is in its most basic form is saying, how far can you drive from somewhere? And an added layer that we do here of how many people live within that distance. So specifically, we're going to look at how many people live within a 45-minute drive of a stroke center in the state of Mississippi? This analysis is based on an actual story that published a couple of weeks ago, a collaboration between Kaiser Health News and Investigate TV. It was published a few weeks ago, and we looked at the Mississippi Delta and Appalachia in total, so a whole bunch of other states as well and other regions. For this presentation, we're just gonna look at Mississippi to make it a little simpler. Now, there's a lot to get through. I'm gonna have to simplify or sort of gloss over a couple things rather than going line by line in all of the code. But I want to talk about really the concepts that you have to do, and then the code is here for reference too, of course, so you can always come back to it. And I do want to leave some time for questions after each section and at the end. So if there's any parts of the code that you want to go over in more detail, I'm happy to do that. But particularly some of the mapping code, we just had a nice introduction to how to do that and looking at maps in R. So I'm going to skip a little bit over the code for how we're mapping and talk more about what we're looking at. So to figure out how many people are within a certain distance of a thing, the basic process that we need to follow is we need to get a data set of locations we care about. And for this project, I'm providing that. We're going to use the one we used in the story, but you could look at colleges, you could look at grocery stores, any kind of thing. And then number two is where we really start getting into it. We need to get a drive time isochrone for each point. An isochrone is basically a shape that delineates how far you can travel in a given amount of time. We're going to look at 45 minutes because that's a meaningful time when we're talking about stroke care. You kind of want to get to the hospital within that amount of time. And if it's going to take longer, you might want to go to a different hospital. So we looked at 45 minutes. I will note, you'll see different words thrown about: isochrone, isoline. Isochrone has to do with drive time. Isoline is more general and usually has to do with miles driven. But roads don't follow miles, so you could be 2 miles away from something and it takes a lot longer to get there than somewhere 5 miles away if you have a lake in between. So we care about driving time, not about miles, for any kind of spatial analysis. Then the next step we need to do, which is where it gets really complicated and fun, is calculate how much of a certain basic geography intersects with that drive time area. So here in the US, we're going to be using census block groups. If you're in another country, whatever your country's equivalent is. But basically, we're saying we have this area that you can get to in 45 minutes. To calculate how many people live in that area, we sort of have to break that area into small units of geography. The one that makes the most sense in the US is a census block group. It's a small geography, but not so small as census block. We have American Community Survey data for the census block groups, such as total population, population by race and such. The blocks, which are the smallest unit of geography, are only in the decennial census, which is now 10 years old. We don't have 2020 data. So I think census block group is a geography that makes a lot of sense to use. We need to get the population data for that block group. And then we basically multiply some things by each other. So we have 5 main steps. I'm going to go through each of them, how we're doing them in R. And like I said, I'll try and pause for questions a few times, and certainly at the end, if there's anything in particular that you want to go over in more depth, but I want to be aware of time. And one important note, drive times vary based on real world conditions like roads or a bridge closes. That can really change things. So I use the isochrones here that we used in the actual published project. All of them are available in the GitHub repo, which the link is up here too. I'll click the link. You can see the link here. So the GitHub repo has all the data that we're using in it basically. And yeah, so just a note, if you were to run this tonight yourself, you might get slightly different results because the real world driving conditions were, this was run several weeks ago. We have a question. How did you get the stroke care center's data set? So a stroke center, I should have explained this. That's a good question. In the United States, there are several bodies that certify hospitals for their stroke care. So any hospital can treat somebody who has a stroke, but there are different levels of care that hospitals can provide. And bodies like the Joint Commission and a couple others have these sets of criteria that say, if you perform a certain number of these procedures a year, if you meet certain requirements, we'll certify you and basically give you, a thing that you can tell people. You can tell people we're certified as a comprehensive stroke center. And it has meaning for emergency medical technicians, they'll send people to a hospital that has a certain certification. So yes, any hospital can treat people, but the certification basically says we meet these requirements of care. And if you're having a very severe stroke, you definitely want to go to a certified stroke center. Okay, so into it. This is a list of packages that we use in this project, some tidyverse packages. The core ones for the actual spatial analysis side are SF and Leaflet, which you just got an introduction to. Tigris2, Leaflet, and ggplot are really just for mapping purposes, not the analysis. And then 2 API packages. The here_are package is a wrapper for the here geospatial technologies tool. Basically, here is a company that, it's a rival to Mapbox or Bing or Google Maps that has geospatial analysis capabilities. And they have a decent freemium tier if you're looking for a provider that does something like this and your newsroom doesn't already have a contract with one of those other ones. Here works out pretty well. This project is really small, so you would not exceed the freemium tier. And then we use the census API package to get census total population data, which also requires an API key. So this is part of why I'm not running through this live. There's some complex steps, and also we'll get to some code that takes several minutes to run. So I definitely don't want to run something for 10 minutes of this presentation. Okay, so starting off the project, we load our libraries, read in our data set. And again, I'm not going to go into all of this code, but here's what the data set looks like. It has hospital name, an ID number, who's the certifying body, which isn't relevant today, but also state and address and stuff. You're welcome to look into that in more detail. And then we get into the stuff we just learned. We're going to take our points and make them into an SF object. So we're taking that latitude and longitude and giving it a projection so that we can do some stuff with it and so we can put it on a map. So here's just a quick, simple little map of our stroke data set. Again, our project looked in the Mississippi Delta and Appalachia, so it does not cover the entire country. We basically had to make this data set by hand, so no need to get into California if we didn't have to for our story. So this is the full data set that we're looking at. Now, we're just interested in Mississippi, so I don't need all of these Northeast stroke centers. I don't need to get drive time distances for all of those. So what we're going to do next is filter our stroke centers. So this is kind of the start of the real spatial analysis. So we're going to go back to the Tigris package and get states. And you'll note here, I'm not using the option that Aaron used in the last package of this CB equals true. That's the cartographic boundary shapefile. Those are simplified shapefiles that are good for mapping, but not good for analysis. When we're doing any kind of spatial math, you want to use a high fidelity file and one that's not been simplified for design purposes, because we're not just making a map here, we're doing math on it. So we get our state shapefile and we want to filter it to just Mississippi. And then I want to give it a projection. And I have a note here with a link you can click if you want to learn more. And frankly, I'm not an expert on this intricacies of the SF package, but for doing math with the SF package, you need to use a planar projection, which is a spherical projection that assumes the Earth is circular. This is different from a lat long projection that you need to use when you're making a map in Leaflet that uses lat long coordinates and sort of treats the Earth as flat. If you use one of those projections with SF, it will work, but you'll get this angry warning message, and you really should use a different one. And again, I'm not an expert in this, but I've read all the documentation and like all the Stack Overflow things on this, and I agree with the suggestion that you should use a planar projection. So you'll see in this project, we use this 2163, a spherical US projection for analysis. And then when I go to map things in Leaflet to make sure I'm doing things right, I go back to a lat long projection. It's a little bit of a hassle, but there isn't much way around it that I've figured out. But if any of you have figured out how to like use the same projection for both, let me know. Okay, so now what we want to do is we have all these points in the whole Eastern US, and we only want the ones that are near Mississippi. So what we want to do is make a 100-mile buffer around Mississippi and just choose the stroke centers that are within that. So that is, you can see here in this map, there's this blue line around the state, and then there's this red blob that extends 100 miles out. So the code for that we used for that is really simple. It's one line. It's called the st buffer function from the SF package. And we just say distance equals 161,000, which I Googled 100 miles, 2 meters, and that's what it told me it was. You can always check, look up your projection number, and it should tell you the units. If it's in feet, you may need to change that. So I recommend just like using a meter projection to make it simpler if you're going to be doing anything like this, because you don't want to get into like a unit confusion situation. So I just made a simple map of this to make sure that my code made sense. So I mapped my state, my boundary, and all the points. And it does make sense. We should be getting all these points that are in and near Mississippi once we filter. So we're going to use this simple code that combines some straight up dplyr filtering with SF. Now we're going to use a function called st-intersects. And we're going to say I want the intersection of my stroke center geometries and this red buffer around Mississippi. And that returns a much smaller number of stroke centers that we can run our analysis on. So here I just tabled the state on those centers to make sure that it makes sense. You know, none of them should be in New York or Pennsylvania because that's too far away, and it does make sense. You'll see in this tutorial there is a lot of let's stop and verify that the thing makes sense. I think that's a really prudent thing to do, especially if you're working with packages or techniques you're not as familiar with. You know, put it on a map, run summary things, do checks on your data to make sure that it's valid every step along the way. Inevitably, you'll do something wrong and it won't make sense and you'll end up on the other side of the world, and you know, better to catch that earlier. Okay, so we have our filtered stroke centers. And now let's just put them on a map again. And it does make sense. Now we only have ones that are in and around Mississippi. Oh gosh, zooming in on the map accidentally. And so now we're ready to move on. So if anyone has questions about this, why don't you write them in the chat or hold them to the end? I want to sort of get through the main components and then we'll go back if anyone has questions or things we want to go back and look at. So then the next part of this analysis is to actually get the drive times. So we're going to use the here.r package, which is a really nice package that wraps the Here Technologies API. So you don't need to write your own API code. You don't really need to understand the inner workings of the API, just the here.r package. And I will say, as I was working on this, the actual project that this is based on, I ran into a couple of things with the here.r package where the underlying API had changed. And I was like, can you add this option? And the developer responded within like a day or two to everything, sometimes within a couple of hours. So I really like this package. The developer is really responsive. It's really nice. So I'm going to first show you, I'm going to scroll down a bit and show you the actual code, and then I'll go up and say how I'm using it. Let's see if I can highlight this so you can see. So the actual code to get a drive time radius is pretty simple. We use this function called isoline, which remember is the sort of more general term for this type of thing. We're going to give it POI is like place of interest, point of interest, I think. We're going to feed it a location from our Stark Centers data set. We're going to give it a range, which is how much time are we interested in, which is 45 minutes, and it's in seconds. So we do 45 times 60. We care about time, not miles of distance. We want to do car, not like public transit or walking. We want to optimize for quality of the results, not performance. I don't care about it being super fast. And we have a question here, a good question. What is the rate limit? So they started rate limiting this while I was developing the code. I just went back one day and ran into all these errors, and that was not fun. So the freemium tier allows like 250,000 calls a month or something. Like it's a very high number, which is one reason I went with it. You can't really get something like that from any of the competitors. But they now have this rate limiting like time thing where you can't make 1,000 calls a minute if you're on the freemium tier. So what I do in this code, and you'll see it later on, is I give it a little blip before. So I run one location and then I give it a little pause and then another location. And actually, as I was developing this, at first I had used 0.15 seconds between it. And then I was doing this like over the weekend running this code, and then I was getting the rate limit errors again, which is status 429. And so I increased it to 0.4 seconds. And that works now. So, you know, your mileage may vary, I guess. I don't know. And maybe it was just my computer was really slow before when I was doing it, but then my internet was fast this weekend. So, yeah, rate limits and pricing is part of the reason why I went with here. The other reason is Google, Bing, Mapbox, they all have these restrictions. If you want to map your data, you have to put it on a map made with the same provider. And I don't like that restriction, and here does not do that. I can't put here data on a Mapbox map legally, but I don't care about that. But I can put here data on like a data wrapper map, or just a map that I made myself and not have any questions about it. And it's sort of a gray area with like Mapbox. Can you put it on like map made in Illustrator? Questionable. So yeah, I used here for those reasons. So this is the code for getting the isochrones. Like I said, it's really simple, but I will say now, sort of like zooming back to this whole function, what I do that some of you might be familiar with, some of you might not, is I put it into a try catch function. Like I said, I was running into some errors when I did this. Basically, try catch is a technique in R and in other programming languages of the thing I want to do is get an isochrone for one point. But if it fails, I don't want it to break my entire program like this. And this is going to take several minutes. I just want to hit run and then leave and I'll come back. And so I don't want it to run into an error and then completely stop running. I want it to try to get the isochrone. And if it fails, I want it to give me a message. So print to the console, like the ID number that failed, a little message. And then what I also do is I make a little data set that has the hospitals that failed in it. So if I want to go back and rerun over just the failed ones, I can do that. And this ended up not being necessary, but when I was first developing it, and there was like a couple little things that the Here package developer has now fixed, I did actually need this because I was having some issues in like Connecticut with my points. So I have a link here if you want to learn more about try catch. That could be its own talk entirely, but there's a link here to a like book chapter. Hadley Wickham wrote about it, so you can learn more. I highly recommend, especially with anything from the AP, from any API, if you're like running a whole bunch of things through it, and any code that you want to like let run overnight or anything, definitely want to write in some error handling. It is worth the effort. So in the end, putting that all together, what it looks like is for each of my stroke centers, just print the number, give it a 0.4 second delay, and then filter to just that hospital, try to get the isochrone for that hospital. If it doesn't work, save it out to this error data set. And if it does work, add it to my data set of isochrones. So assuming everything works well, it just goes one by one through my data set, get the isochrone, give it the information, and join it all together. You can feed multiple hospitals or locations into the here are package isochrones function. What I don't like about doing that way is, number one, when I was first doing this, it didn't have the rate limit thing built into it, so that was failing. It does now. I have not tested it out, but like very recently, it has rate limiting built in, so that the rate limit accommodation built into it. But it also doesn't make it easy to like attach data to it. It doesn't automatically like bind the attributes of your location to the isochrone that's returned. So I'm like, okay, I have this data set of isochrones, but I don't know which is which. And I really need that information. In the actual published analysis, we also sort of like stratified by type of stroke center. And if I didn't know which isochrone belonged to which hospital, that wouldn't have been possible. So there are different ways that you can do this step. If you don't need stuff like that, you could just send the whole batch in one go to the Here API. But for my purposes, doing it one by one and attaching that data and making sure I wasn't having rate limit issues was something that was the best decision. So now I have my whole data frame of isochrones, which is an SF object, and I want to join just like some plain attributes to it. So I want to join the hospital name and the county and zip code and things like that using the shared hospital ID that I attach to it. So I just do a standard old left join and clean up the data frame a bit, remove some columns I don't need, such things like that, arrange it by state and city. And then here is the results. I put it on the leaflet map, like I said. When you're doing anything spatial, put it on a map frequently, make sure you're doing it right. So each of these little green blobs is a 45-minute drive time radius from one hospital. So you see if I zoom into Birmingham, it's dark and there's all these sort of overlapping blobs, and that's because there's a whole bunch of certified stroke centers in Birmingham, most like major cities. That's where the most stroke centers are, especially like the top tier certified ones. So you'll see there's a lot of areas of Mississippi that don't have a green blob, meaning they're more than 45 minutes away from a stroke center. So here, right away here, if you're just making a map of what parts of my state are within a distance of a location, you could stop right here. If you just want to say like, what parts of Mississippi are within 45 minutes of a vaccine provider or something, you could just make this map and you're done. So that's really powerful in and of itself if you're just talking about geography, but we also want to talk about people. How many people live within these green areas and how many people live in the white areas? And if you know anything about geography of Mississippi or about the US in general, you'll know most people live in more urban areas. Like a lot of people, there's a lot of areas of the state here that don't have a stroke center that are very low in population, or it's, a state park, a mountain, whatever, there's nobody living there. But there are some people who live in these white areas and we want to know how many. So the next part, almost towards the end, we want to bring in census data and our census block groups. Now I'm getting short on time too, so I'm not going to get super detailed into this shapefile. All of the details are in the original repository. I used a national block group shapefile from the NHGIS, which is already clipped to shorelines. And then I had to clip it to interior water as well, using shapefiles from the USGS, the National Hydrography data set. This is the step that I had to do in QGIS because it completely aborted my R session. It was terrible. It like made my computer overheat so badly when I tried to do this in R, and then everything froze and died, even when I just tried to do one state, let alone a whole bunch of states. So that was the one step that I could not do in R. I had to go to QGIS. It was really sad, but it took like 2 minutes in QGIS and would not work at all in R because census block groups are very, very small. There are about 2,000 of them in Mississippi, and I was trying to clip them to lakes and ponds and such that were basically like any not tiny water feature I was trying to clip them to. So it was a lot for R to handle, but QGIS handled it pretty well. I very much recommend clipping your shapefiles to water for this kind of analysis, unless you're in an area with a lot of people on houseboats, which is very real in some parts of the world. But we know people don't live in the middle of the lake. And when we're talking about drive times, like, can you get to the middle of the lake in 45 minutes? It's going to affect your results. And if I don't have a screenshot here, but I was looking at like the New York Finger Lakes on a map with the block group boundaries superimposed on them. And, you know, half of a block group in that area is the lake. So if we're talking about how many people, we really only want to focus on areas where people live. So reading in my shapefile that I've already clipped to water and all of that stuff, which is in this repository if you want to run it yourself. We just read it in with that dst read function. And now we're going to take both of our shapefiles, our block group shapefile and our isochrones st object, basically a shapefile. We're going to transform them into our planar projection that I was talking about earlier, which is CRS 2163. And then we're going to use a little function called stMakeValid. This is an important one to know about when you're doing any kind of spatial analysis. You might get some errors saying like there are little holes, or I don't know, just like overlapping lines or things, little things that you can't really see on a map, don't make any practical difference, but will totally throw off the computation stuff. This function stMakeValid takes care of that. It does not simplify it, but it just resolves those like internal boundary differences that might cause an error. So if you're getting errors, try this stMakeValid function. So now we have two shapefiles. We have block groups in Mississippi, and we have isochrones of hospitals that are in and near Mississippi. So we want to know, where do they intersect and by how much? Is each individual block group, is it wholly within the green drive time areas? Is it completely outside of it, or is it overlapping on the border? And if so, how much? So the next thing I do is join my isochrones into one shapefile. So I'm basically taking all these little green blobs. I don't care if you're in green blob number 1 or green blob number 2. I just care if you're in them, period. So I use the stUnion function to make them just into one feature, because I don't care about the individual ones at this point. I just care about like in it, yes or no, and by how much. So that's the stUnion function. And then I use stfsf to give it some more attributes, basically make it look more like a SF object, because otherwise it's just geometry, since it's only one polygon at the, or one multi-polygon at that point. So I'm going to show you what that looks like. Again, we remember we had all these overlapping green blobs before. Now we just have one. So even in Birmingham, now it's just like one shape of all the shapes joined together. And now here's the real math. And this took some figuring out. I read all of the Stack Overflows and tried so many different things to make sure I was doing this right. Now we need to calculate the percent that each block group overlaps or does not overlap with these green isochrones. So the first thing we need to do is calculate what is the area of each block group. And that's really simple. We just use the stArea function. So I'm saying in my shapefile, make a new column called block group area. That is the area of the thing. And then I want to calculate the intersection. So I'm going to make a new data frame, basically a column that has the intersection between my block group shapefile and my isochron shapefile for each and every row. I'm going to make a column called intersect area. That is the area that's shared between the two of them, and select those two columns. So I have the GeoID for each block group and the amount of the block group area that overlaps with the isochrons area. So if it's completely inside the isochrons, it's 1. If it's completely outside of it, it's 0, 0% overlap. And otherwise it's somewhere, oh, I'm sorry, not 1 and 0. We're talking here area still. So it's, the amount of area that is inside of the isochrons is what we're calculating here. And then I join it. And then something went weird with I don't know why this is so tiny here, but I want to join that data frame to my block group shapefile. And then I calculate the overlap. So I say it's that intersect area that we just calculated divided by the total area in the block group that we calculated a few steps up. So again, the overlap, this percentage that's from 0% to 100% or 0 to 1, we're calculating it as the area of the block group that intersects with the isochrons divided by the total area of the block group. So it's a really simple computation. We don't have to write like lines and lines and lines of code. And it just takes a few lines using R's SF package to get there. In something like QGIS or ArcGIS, I'm not totally sure, but I feel like this would be more complicated and it would definitely take longer to run. It's kind of funny, the clipping to water completely broke my R, but something like this only takes a few minutes. And then I want to show you what that looks like because I know this is a really complicated concept. So here's another map. And this also too was like really hefty for R to map. And so that's why it's a screenshot here instead of interactive. But here, all these little tiny black shapes are the census block groups. And what I'm coloring it by from like white to purple is that overlap percent that we just calculated. So you'd expect if it's 100% overlap, it's dark purple. And so any block group that's entirely contained by an isochron is 100% overlap. Entirely outside is 0. And on the margins, it's somewhere in between. So what you're seeing mapped is exactly that. If it's entirely inside the isochron, it's dark purple. And this is just sort of verifying that I did it wrong. Like if I saw just random purple all over the state, I would know like, oh God, I did something so drastically wrong. But this verifies that what I was trying to do, it did work out. And then I am like running out of time, so I'm going to skip getting this, but I got some block group populations from the Census Bureau. You can look at the code to see the line of code that did that with the Census API package. And then I'm going to join that to my block group file. And then it's a really simple multiplication. So I know how many people live in my block group. So I know my total population. The population that are within, we're just going to use that overlap percentage to multiply it by. So we're going to say if 60% of the block group's area is within the drive time, we're going to assign 60% of the population to live within that. Now, we don't totally know that like population is equally divided within a block group. It isn't like, if there's going to be big housing complexes in one neighborhood and like a school in another, but it's sort of the closest we can do. So we assume that it's equally distributed throughout the block group. And then we just take the total percent of our area that we care about is that number that's within it divided by the total. We do that for the state of Mississippi and we get 68% of the state of Mississippi is within the green isochrones and 32% is not. I know I just said like 8,000 things that could each be their own tutorial. I'm not sure if I have any time left, but if we do, I'm sure some of you have questions and I'm happy to go over any parts of this that you want more detail on.
Anyone have one quick question? Otherwise, we can go to the news nerdery to thread questions.
Oh, and Sharon, to your point, the actual analysis that this didn't publish, it didn't end up being relevant, but we did actually look at Black versus white too within distance district centers. So if you're interested in the demographics too, beyond just like total population, you can check out the GitHub repo for the actual project, and that shows how to do that stratification at the end. It only has to do with this very last section where you're actually like doing the math. The spatial stuff is the same. You're just joining like multiple population categories, not just total. Okay, unless we have any questions.
Very cool. Spatial
Thank
analysis
you.
is so powerful. Thanks so much for doing this great walkthrough.
Thank you.
Okay, so I'm going to kind of pivot to this other weird, it's very niche. I was surprised that this got voted on, but I'm happy to walk you through kind of my process of creating a, I guess, well, pretty much I'm going to be talking about Docker and R, but the whole gist of it is how to really quickly spin up an R server. All right, so you can host R Markdown files, Shiny apps, or even an API. So let me see, my turn. All right, so I'm just gonna go ahead and say right up front that I am not like a systems admin person. I really don't know my way around Unix or Ubuntu or whatever, any of those things. So everything that I'm showing you, I've kind of like scrabbled together by like pouring over Stack Overflow and just Googling everything and just finally at least gathering all these different pieces to like move stuff around so that it like eventually ends up online and it's being served. There's still probably so many things, like if I sat down with an engineer, I could smooth things out. And oftentimes really the big secret to getting an R server up online is yeah, working closely with an engineer. So Docker and R, let me put the slides in. All right, so the slides and like kind of a long walkthrough. I'm really explicit with a lot of like bullet points, but I'm not going to go over them specifically because it would take forever. So it's all there for you to look at later on. But kind of overall, what is the point of an R server? It's so that you can host stuff like Shiny apps. So you can host your R notebooks. You don't have to publish to GitHub pages. You can just put it internally. It's great for Learn R tutorials. There's this new kind of R Markdown that's kind of really advanced, where it kind of becomes like DataCamp or Coursera. In these other courses where like, this is all run by R Markdown, but you can type in the code and grade students on it. So like filter species equals beluga whale. And then I can run it, and then it'll say, nope, wrong. Did you mean to put that? And you can run it. If they get it right, then you can click on continue. And it kind of goes on next to next. So that's like really useful for a lot of educators out there. You can also run RStudio Cloud. So instead of RStudio locally on your computer, you can run it on the cloud. So this could be useful if you want to just spin up a server for really with a ton of cores and a ton of memory, so that you can really handle wrangling a bunch of big data instead of running it on your computer where it will crash. You can also use our servers to run an API with the Plumber package. This is what we did with Arcos and the Washington Post data. So we instead of like creating an R package that would run off of like internal data, we created a layer of an API that would then run into an R wrapper package, and then it could also run into like a Python package which someone wrote. So it's like one extra layer of data distribution, but allows for more wider reach. And this is something we've used as far as Plumber goes as an API. We used it in the recent election Lenny, who was just talking earlier, he put together a kind of a combination of using Python to munch some data. He also then used the R model and piped that all in together to put out predictions, live election predictions onto a JSON that then ran the page, the election page, and you can see the little fuzzy bar chart, with the confidence levels and stuff. So that's how we've been using it so far. So okay, so what are your options if you want to put this online? If you want to put an R server up? Well, number one, if you're doing R Markdown, you can just publish it as an HTML file and publish it through GitHub pages, free. It's great. If you want to try to host your own Shiny apps, it's not as free. There is a free site. You can get 5 apps. And then they measure it by how much time is people are using it, because literally it's a server that is running every time you use it. It's not that great as a front facing app. You could never put this on a news site and let thousands of people, millions of people hit it. It would completely crash. So they're not there yet as far as the technology is concerned, but internally it's great for data exploration and sharing with reporters and editors. And so, our studio, they want to charge people. That's how they make their money, is they create these open source tools, but then they create these cool little things that let you upload it to their servers really quickly. And they gives tech support and everything. So what they do here is they add this little button where it's publish, and you can publish your Shiny app and it goes automatically and updates everything. So it's one click publish. So that's how they make their money. But we're journalists, we can't afford that. So we try to scrape and run it ourselves and build it from scratch. And so if you do want to host it yourself, there's quite a few options. You can use DigitalOcean, that's just a regular server company. And these are all links to how you can use it yourself from walkthroughs that other people have created. I have a link to you can get $100 credits. I think the cheapest droplet you can use is $6 a month to create your own server. Otherwise, you can use Heroku, and there's a free tiers you can use. AWS and Google Cloud Run, those are all options you can use if you would like to host it yourself. Okay. At the Post, at least for me, I use DigitalOcean for personal use because I've just been using DigitalOcean forever for hosting. And at work, we use AWS hosting, which is, and it kind of so Docker plus AWS is how we do it at work. And so, so for DigitalOcean, it's good pricing, good documentation, one-stop shop 1.0 for storage domains. You can set that all up. You can even sync it with Dropbox for easier file exchange if you're doing an RStudio server. And then if you use AWS at work, whatever your news org work uses, hopefully you've got great engineers to help back you up when you run into issues. And of course you can host internally, and it's the company's paying for it, you're not paying for it. Okay, so if you were to set up an R server on DigitalOcean by itself, minus Docker, these are all the things you would need to do. It's like I said, it's all sysadmin stuff. You got to create a droplet in DigitalOcean. You got to choose an image with at least 1 GB of RAM. And so what I mean is, so you go to DigitalOcean, and let's say you click on new droplet. And droplet is just these, what they call servers, whatever, spin up servers. So you can click on create, droplet. This is where you can set the options for what you want. Whatever image, you can choose plans, what CPUs, and automatically they say you want the $48 a month option. It's no, I just want the cheapest option, at least 1 GB RAM of memory. Depending on if you're working with spatial data, you probably should, get something a little higher, but this is only per month. And then, data center and other SSH stuff. So you just kind of set up that, you spin it up, you get the IP address, you select your SSH security, you get your own floating IP address, and then you have to go through your command line to go in, set up your security, your password, and then, a bunch of other sysadmin tasks like, setting up a user, setting up SSL certificates, and then writing the configurations for all the ports. And then you have to go inside and then you have to actually manually install R. Okay, you have to update all the packages and apt and install the base. And then you got to go and move over like all your R scripts. You have to install every package for it. And so you can move a script over that has all the list of packages that you want to install through R, and you run that script. And then you have to set up the server based on what you want to install more Shiny stuff, the Shiny packages, set up the appropriate ports to listen to. And then, if you're doing a Shiny server, if you're doing RStudio Cloud, then you have to install this other package, create users for folks to log in. And if you're doing like a Plumber, then it's like all these other packages. So it's just installing, and then, making things public and shifting things around. So that's what you're doing if you have to do it by hand, if you do it from scratch. And I'm saying you can simplify that process using Docker, okay? So Docker is like, if you got to think about like brewing and drinking beer, and Docker honestly might be like the future of, maybe the future of like reproducibility, because it's kind of like virtual machines where you kind of, you start out with a Docker file and that describes the steps needed to create an environment. So a beer recipe. And then you've got the image, which is like a script. When you execute the steps in the Docker file of the script, the recipe, you build the Docker file, which contains the environment that is perfect for what you're going to run. That's the batch of beer. And then you get the registry, which stores the built image so that others can use them. And this is like a liquor store. And then finally, you've got the container. So you, at a specific moment, you can start a container from the image, which amounts to running a process in the built environment. So it's like drinking a pint from the beer. And so you can easily pour a lot of replicas with the same beer. You can pass this Docker image to other folks and they can run it from scratch and then double check your work, get the exact same process that you did. So the bartender, which is a server, is decoupled from the beer we want. We don't have to go to a brewer and brew a new beer each time we want a pint. So the same bartender can offer many different types of beers. So there are different layers in the Docker container, which is like simplified version of what I just talked about when you're doing everything by hand, creating an R server. Is one, you got to set up the base operation system. Two, you got to set up the system dependencies. And then three is like installing R, the R packages, and then code. You got the code, and then you got the data. All right, so this is what a Docker file looks like. You start out with just one line, which is from Rocker Shiny. So these folks, all it does is you've got all these like Docker files. Hold on. Docker setups. So they have all these images. So you can set up a lot of things people have already created already. Python environments, JavaScript optimized environments. And so some folks have gotten together, open source folks, and they said, these are the things that all the lines we've collected to start running on our server. And all you need to do with your Docker file is just put this one line. Say, I want a Shiny server. So this is it. And so it'll pull from it. Kind of like, install.packages. This is exactly what it's doing. It's installing the whole Shiny environment for you. And then you got to put in your system dependencies, like as a script. And so I want to update these things. I want to update these files. I want to install Git, all these different things. So it's just a lot of people have already kind of set these files up for you. So you can just kind of like copy and paste. This is pretty much what I did, and we'll see what works for you. And this is essentially the environment that I'm working on, and is just in our stuff. It's you got the depends file, which is all the R packages stuff. You've got the Docker file, and then these are the things. I've got notebooks and I've got a Shiny server. That's all I'm putting into my Docker file. And so then I have to put in my Docker file, like I need to start a work directory called Shiny server. I'm going to copy, I'm going to tell it like copy these files over, move this R script over, run that start R script to install the packages, move these notebooks over, copy it over, create this folder, copy these 2 files, server and UI for Shiny. And then I've got another file called docker-compose.yaml. And so that just pretty much I can pass on arguments to it to tell it like what version, what ports to open up, and a bunch of other things. Like if I wanted to do other type of servers, I could list them here. And so then once I have all those elements in here locally, let's see if I can pull that up. So I'm just working normally in my local environment, and I've got like, here's my Shiny. I'm going to run this, and this is just running running some data from the Washington Post GitHub file on police shootings. Okay, so this is just downloading straight from GitHub, and it's building up an Explorer, and it's installing everything. Just thinking, okay, so these are just police shootings in Florida over time. And so like this is a normal Explorer that you would want to create. And then you've got table to let folks explore. So this is just a regular Shiny app. Okay, so now let's say I like all this stuff. I want to move it to an R server so people can look at it. So that's why I create this Docker file where I install that line. I set up the system dependencies. I create the folders and I move the folders over. And then finally, I do an expose 3838 for that. And so then what I do next is I need to install Docker on my computer, and then I can run it locally. And it'll run here. It'll take a while to build, but fortunately, after you build it once, it'll like cache a lot of it. So it won't take forever. The longest thing that takes to run is like installing tidyverse. You can see this is how long it took to build things, like to run scripts. Like this one took forever. All those R packages that I have. So I want to run it locally, and then I can see in here in my Docker dashboard how it's running. I thought I had it opened up earlier. And so then I can see all the images I have, what's running, and I can explore it. And like, I don't remember what the address is, so I can just open it up through the browser. And so this is like the Shiny one. So I'm going to just do /Shiny. And so now it's running locally. It's going to take a while to run. And I can see how it's like even running in the background. Okay, it's a little slow with Zoom. But trust me when I say it'll work in a second. So let me go back to here. Okay, so this is what it would look like running locally. Okay, so the next step is to move it online. Okay, so first I'm going to upload this repo, this local project, to GitHub. Okay, so then it exists right here. All the files, including the Docker file that I've written out. And I've double checked that it works locally when I run it. Okay, so next step is sign up for an account on hub.docker.com. Now this is at work, we have these other systems that we use something called Jenkins that like tracks Docker files, containers. And so what you can do is you create a Docker repository there. And then I named it the same thing. But what's interesting is at the bottom left, you see there's something called connected. You can connect your GitHub account to this Docker repository. Okay, once you do that, you can say, I want this Docker repository to reflect and be connected with my GitHub repository. Docker, same name, just to keep things consistent. So I connect those two together, and I say, and then I set the settings to be like every time. So now every time GitHub, I push a change to my GitHub repo, the Docker file will automatically rebuild. Okay, so that's wonderful. It's just one less step. And so then you build, so builds are now connected to GitHub activity. And so then you've got those two steps. Now you need to set up your server. Okay, so you can go back to DigitalOcean or AWS or Heroku or whatever you use. And fortunately, there's one click button for creating a Docker specific, all the files ready for Docker in DigitalOcean. Just click on the create digital Docker droplet. And then once it's all set up, then you can, reselect the pricing points and how fast the server you want it to be. And after you do that, you can just log SSH into that server that you just spun up. And you can set up the name, domains, and everything through DigitalOcean and whatever. And then all you have to do is just write these two commands. You tmux in, because what you're trying to do is you want to set up the R process that are running at the same time. So like after you close out, like the R server will always constantly be running after you leave. So you just do these two lines, Docker tmux, and then you just do Docker space run, and then you set your ports, and then you just do ab-trans your name, your Docker hub name, and then whatever your Docker was, your repo setup, and you do :latest, and then it'll pretty much like what you did was as a build on Docker locally. It will download everything and build it there. So you're deploying your image on here, and then it'll run. So then you carefully exit the server. You detach the tmux session by just typing Control-B and then D, and then you can visit your page online. So this is what it looks like locally, and this is what it looks like online. Okay, and this also works with, what was it? Notebooks. So I had a couple of R markdown files here in the notebooks folder. So one RMD here, and it will generate it. It will ignore the HTML file and just kind of rerun the RMD file from scratch. And this is taking a while because I did not optimize it. I told it to download from GitHub every time it loads. And then, yeah. Okay, there it goes. So Fatal Force notebooks. So now these notebooks are shareable to folks. Okay. And so every time you need to manually update and redeploy, you need to manually redeploy every time you push a new change to GitHub and changes. Can you run Docker on a droplet already has a starting server running? I think so. Yeah, I think I have a droplet that has like a bunch of different servers running. You just have to have a different folder for it. And that's it. And so this is like it. It's like 30 lines of code to start a server, copy some files over, and then run it. And you've got it on droplet. I'm sure you've got your own R server. All right, so I know that was really rushed, but I wanted everyone to get through by the end of the day. But all these files are there. It's kind of hard to do it unless you really start diving into it. But hopefully the files that I left will give you a head start. The great thing about Docker is you can set like the versions of packages you install, versions of R you install, so that it will always maintain that image. Do I need to regularly change my setup code there? Honestly, every once in a while, because like I think the latest thing was like somehow like spread to pivot wider, like broke a couple of my servers, so I had to go back and fix that. So I mean, yeah, some changes will make things mess up. All right, so yeah, that was very niche. Now I'm going to switch over to what Byron sent us. He sent over a video because it's his birthday and he's celebrating with his family. So he's very kind to send over this video that we can play for him. All right, let me spin that up. Okay, please let me know if the sound is okay.
Hello, I'm Byron. I'm a developer for the CNN Visuals team based in London. And my confession for this R unconference is, I don't know R. Not very well anyway. But I absolutely love using it. And what I found out quickly is that I need to automate things. So that's why I'm here, to show you how to automate with GitHub Actions. I think the best way to explain is with a little project. So I wanted to automate a script that could fetch and save data, create a graphic, and do something with it. So now once a day, my script runs and retrieves US vaccination data from our world and data. It draws an arc for each of the 50 states based on the % vaccinated, with the hope that soon all 50 circles will be complete. And then it posts the graphic to Twitter where no one notices. Okay, so maybe tweeting data art into the void isn't going to help you at work. But maybe you're working on a story where data is constantly changing. Automating a script to update a chart and push it to a Slack channel might not be such a bad idea. Or maybe you need to set up a few scrapers and you don't want to get the whole IT department involved. So here's how you can set one up. Inside the repo, I have the main R script that I want to run. When it runs, I'm also saving a CSV in the data folder. I'm not saving the graphic that gets created, but you could if you wanted to. I just want to point out here that I've separated the package install into its own file. So to automate this, you create a special directory path called .github/workflows. And in that path, you create a workflow file. The file is the name of your workflow with a .yml extension called a YAML file. Don't worry if you've never worked with it before. This is what the YAML configuration looks like. And this is what we're here for, so let's take a closer look. Each workflow has a name, and then you set up when it should run. I've chosen workflow dispatch, which means I can click a button and run it manually, and also schedule, which uses the cron syntax. We'll come back to that in a minute. There are other events you can use to trigger the workflow, things like pushes and pull requests. Check the GitHub docs for the full list. So I only need one job for this workflow, but you could have more. You choose the operating system you want, Mac, Windows, Linux, or Docker container. And this is optional, but you can set up environment variables, which I've set up as secrets under settings in your repo. Okay, so this next section is just the series of steps it's going to take. The first step is a pre-built action from GitHub that checks out the repository. Then one from rlib that sets up R specifying the version. Now we want to use a cached version of this virtual machine if we can. I give it a key that uses a hash of the contents of that install.
All right, I'm gonna try this again. How can I make this better? Oh, is that better? Wait.
It looks better right now, anyway.
Okay. I have a feeling when I press play, it's gonna get bad again. Let's see if I can maybe switch to desktop. Okay, I'm gonna press play and see what happens.
Packages file. You don't have to use variables like this. You could give it any name you want. But this way, if my dependencies change, it will create a new cache. And notice I've given this step an ID. Steps can pass information to other steps. Install packages. You can put conditionals.
I'm going to rewind
in
a bit too.
And in that path, you create a workflow file. The file is the name of your workflow with a .yml extension called a YAML file. Don't worry if you've never worked with it before. This is what the YAML configuration looks like. And this is what we're here for. So let's take a closer look. Each workflow has a name, and then you set up when it should run. I've chosen workflow dispatch, which means I can click a button and run it manually, and also schedule, which uses the cron syntax. We'll come back to that in a minute. There are other events you can use to trigger the workflow, things like pushes and pull requests. Check the GitHub docs for the full list. So I only need one job for this workflow, but you could have more. You choose the operating system you want, Mac, Windows, Linux, or Docker container. And this is optional, but you can set up environment variables, which I've set up as secrets under settings in your repo. Okay, so this next section is just the series of steps it's going to take. The first step is a pre-built action from GitHub that checks out the repository. Then one from rlib that sets up R specifying the version. Now we want to use a cached version of this virtual machine if we can. I give it a key that uses a hash of the contents of that install packages file. You don't have to use variables like this, you could give it any name you want. But this way, if my dependencies change, it will create a new cache. And notice I've given this step an ID. Steps can pass information to other steps. Install packages. You can put conditionals in steps, so we only need to run the install if we couldn't locate the cache in the previous step. So now we can run the actual script. And since I also save the data when it runs, I want to commit those changes. I'm committing as an automated user so it doesn't blow up my GitHub activity. And that's the workflow. So here, that's what's going to run at 46 minutes past the 20th hour every day. In other words, every day at 8:46 p.m. UTC, or if I publish it manually. Don't worry if you're not familiar with cron syntax. crontab.guru website will help you out. So now, since we created that file in the .github/workflows directory, it appears in this Actions tab, along with a history of each time it's run. You can view an activity log and drill down into each step. The slash next to the install packages shows it was able to skip that step because it found the cache in the previous step. And if an action fails, you get an email alert, which is pretty handy. And you can also dig into the logs to see what went wrong. With actions, you get a lot of computing time. If timings are super critical, then you might need a different solution. These roughly run when you set it, but it could be as much as 10 minutes off. Not that you'd want to use something other than R, but anything's possible. You're already in GitHub, so you can just save and commit files. You can post things to Twitter or Slack, deploy to Netlify or AWS. So there you go. I hope this has kicked off some ideas for you to play around with. Thanks for listening. I'd love to hear what you get up to with it. There are plenty of resources out there if you get stuck. Thanks for having me, and reach out if you have any questions or want to share what you've made.
All right, that's it. I will be sure to upload this video kind of separately to the other ones that we have, so that the resolution will be much clearer for the, I guess, the first couple of minutes. Sorry about that. Anyway, our time is up. Thanks so much to the community, the data journalists who made this possible, and for you for attending and taking your Monday out to see this. This was an interesting experiment. I hope maybe we'll do it again. I don't know. We'll see how. Let me know how you felt about it, or like how we can improve things. But we have all the walkthroughs. It's all in the spreadsheet. So hopefully, anything that you were interested or resonated with you, you can go back and figure out on your own. All right. And we're all in the R channel. And if you have any questions, great. We'll keep sharing ideas. All right. Thanks so much, everyone. Have a great Monday.